Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science settles softly into the background hum of the night. If this is your first time here, you've arrived at a gentle corner of the universe where we explore big questions in small, soothing steps. We drift through the stars together, letting the mind wander where it wants to go, without needing to rush anywhere. Tonight, our quiet journey begins closer to home, though what we'll be talking about lies far beyond the clouds, past the glittering arms of the Milky Way and out into the vast silent dark that surrounds it. Our galaxy is a city of stars floating in an even larger ocean, and the question we'll drift through together is simple but endlessly deep. What's surrounding our galaxy? Before we venture outward, take a slow breath and think of where you are right now. Maybe you're lying in bed, the light dim, the sound of the world fading to a quiet background hum. Maybe you're halfway across the world from where I am, in a different time zone, where dawn is just beginning to touch the sky. Wherever you are, you're inside the Milky Way. Every wall, every breath, every heartbeat, all of it exists within a galaxy that stretches 100,000 light-years across. And just outside of that immense, spinning disk lies a realm we almost never think about. The borderlands, the space between galaxies, the unseen environment that shapes and cradles our cosmic home. It's funny, isn't it? We live our lives on a planet that feels large, orbiting a star that feels distant, in a galaxy that feels infinite, and yet even that galaxy is just one among hundreds of billions, floating like a speck in a vast and mostly empty void. We often imagine galaxies as isolated islands, drifting peacefully through space, but they're not as alone as they appear. Our Milky Way is surrounded by invisible structures, clouds of gas, dark matter, wandering stars, and even other galaxies tugging gently on its edges. It's wrapped in layers upon layers of hidden complexity, like an onion of starlight and gravity. What surrounds it isn't emptiness, but the quiet architecture of the universe itself. So, where are you listening from tonight? Somewhere under this galaxy's spiral arms, beneath a ceiling of atmosphere that hides almost everything beyond it. If you could step outside that blanket of air and look down on our home from far above, what would you see? You wouldn't see walls or borders, but a flattened whirlpool of stars glowing faintly against the dark. You'd see great arms curling out from the centre, where dense clusters of stars shimmer like cosmic city lights. You'd see our solar system somewhere in one of those arms, a barely noticeable point lost in a sea of suns. And surrounding it all, stretching far beyond what you could see with your eyes, would be the faint ghostly glow of scattered light, gas and matter, the subtle aura of the Milky Way's outskirts. If you find this sort of quiet wonder comforting, or if it helps you unwind at the end of the day, I'd be ever so grateful if you gave this video a like and maybe subscribed. It helps this little channel of calm science reach others who might need a peaceful pause too. But for now, let's just keep floating here together, suspended somewhere between thought and sleep, looking out across the edges of the galaxy we call home. When we talk about the Milky Way, it's easy to imagine a fixed, definite shape, like a flat disk you could trace with your hands. But the truth is, even after decades of observation, we don't have a clear picture of it. We live inside it, which makes mapping it like trying to photograph your house from the inside of one of its walls. The Milky Way structure has been pieced together slowly, from the light of distant stars, the patterns of radio waves, and the faint signals of hydrogen gas swirling in invisible loops. We know it has spiral arms. We know it has a dense bulge at the centre, where a supermassive black hole sits quietly spinning. But what lies beyond that familiar structure, the invisible halo that extends far beyond the visible stars, is harder to grasp. That unseen region is where our journey begins. The space surrounding the Milky Way isn't empty. It's filled with dark matter, gas, old stars, satellite galaxies, and magnetic fields. It's where gravity, time and history have all left their marks. You could think of it as the atmosphere of the galaxy, though that isn't quite right. It's not air or space dust in the way we understand those things. It's more like a halo of potential, a region that influences everything within but remains almost undetectable. If the Milky Way were a glowing lantern, this outer envelope would be the soft glow spreading into the night around it. The stars you can see when you step outside at night belong mostly to the galactic disk, the thin band of concentrated starlight where most of the Milky Way's stars live. But beyond that disk, there's a vast, spherical region that contains only a sparse scattering of stars, old, faint ones that formed when the universe was young. Many of these are remnants of smaller galaxies that were swallowed by the Milky Way long ago, their stars stripped and spread like ashes across the sky. Our galaxy, like many others, grew by consuming its neighbours. The space surrounding it is filled with evidence of that ancient feast, the debris of countless mergers drifting silently through space. When astronomers point their instruments toward the edges of our galaxy, they see streams of stars moving together, long, graceful ribbons that trace the orbits of long-lost galaxies and clusters. Each one is a clue to a collision that happened millions or even billions of years ago. The Milky Way has been a busy place, though from here on Earth you'd never guess it. The sky looks still, unchanging, peaceful, but beyond that calm illusion, gravity has been sculpting and reshaping our galaxy for as long as it's existed. Every faint smudge of light, every isolated star on the edge of visibility tells part of that story. The farther out you go from the galactic centre, the stranger things become. The pull of gravity weakens, and the familiar spiral structure gives way to something more diffuse and mysterious. Out there, stars are few and far between, separated by thousands of light years. The density of material drops dramatically, yet the region still holds most of the galaxy's mass. That's because most of what surrounds the Milky Way isn't visible matter at all. It's something else entirely. Dark matter, an invisible substance that doesn't emit or absorb light, but reveals itself through its gravitational pull. It forms a vast halo that envelops our galaxy, extending far beyond the edge of the stars, shaping how it spins and how it interacts with other galaxies. Without it, the Milky Way would simply fly apart. We'll come back to dark matter soon, but for now, imagine how strange it is to realise that everything you've ever seen, every star, planet and glowing nebula, is just a small fraction of what's actually there. Most of the universe is invisible to our eyes. What surrounds our galaxy is not nothingness, but a hidden ocean of matter we can't see, binding everything together like the unseen current beneath calm water. When you gaze at the night sky, you're not just looking outward. You're looking through invisible layers of gravity, through the galaxy's silent halo, through ancient debris and faint streams of gas that stretch like whispers into intergalactic space. And just beyond that halo lies something even thinner, more elusive, the intergalactic medium. This is the gas that fills the space between galaxies, so sparse that if you collected a cubic meter of it, you might find just a few atoms. Yet spread across the immense distances between galaxies, that gas adds up to more matter than all the stars combined. The Milky Way is floating in this medium, moving slowly through it like a ship through fog so faint it might as well be a dream. It's not truly empty, and it's not silent either. Within that medium there are faint signals, radiation, particles, magnetic fields, and the gentle pull of gravity from other galaxies nearby. Sometimes, when astronomers map the region around our galaxy, they find strange structures, vast bubbles of gas and plasma extending thousands of light years above and below the galactic disk. These bubbles are thought to be remnants of ancient explosions near the galactic centre, possibly caused by bursts of star formation or activity from the supermassive black hole that sits there. Our galaxy, it turns out, breathes. It releases energy into the surrounding space, creating waves that ripple through its halo, carrying the history of its most violent moments. Even in what seems like stillness, the Milky Way is alive with motion. It's humbling to think that our entire solar system exists within one of those structures, a region known as the local bubble. It's a cavity carved into the interstellar medium by multiple supernovae that went off millions of years ago. The solar system, along with nearby stars, drifts inside this bubble of thin, hot gas, surrounded by denser clouds that mark the edge of the cavity. The local bubble stretches hundreds of light years across, and though it's invisible to the naked eye, it has shaped the environment of our sun, influencing the path of cosmic rays and the distribution of gas and dust around us. We're literally living inside the echo of ancient stellar deaths. When we think about what surrounds the galaxy, we often focus on distant things, the vastness beyond, the emptiness between galaxies. But the truth is, the layers of the Milky Way itself extend farther than we ever imagined. Its influence stretches across more than 1 million light years, blending gradually into the domain of its neighbours. The Milky Way doesn't have a sharp edge. There's no line where it suddenly stops. Instead, it fades out, its gravity weakening, its stars thinning until it merges with the surrounding cosmic web, the grand structure that connects all galaxies together. You could drift outward from our galaxy for millions of years and never find a true border, only the slow transition from one gravitational territory to another. Somewhere out there, about 2.5 million light-years away, lies our nearest large neighbour, the Andromeda Galaxy. It's roughly the same size as the Milky Way, and it's moving toward us. In about 4 billion years, the two will meet and merge, forming a new, larger galaxy. Between us and Andromeda lies a faint bridge of gas and dark matter, a kind of gravitational handshake connecting the two. Even at this distance, the galaxies are not strangers. They've been dancing around each other for billions of years, tugging softly at each other's halos, shaping each other's motion. What surrounds our galaxy isn't isolation, but connection. Invisible threads linking us to every other island of stars across the universe. And yet, here we are, on a tiny world orbiting an average star, sitting somewhere in one of the galaxy's quieter arms, wondering about what lies beyond. It's strange how the more we learn about our place in the cosmos, the more personal it feels, knowing that the galaxy has no true edge, that it blurs into a larger structure, can feel both dizzying and comforting. It means there's no real boundary between here and the rest of the universe, only distance and time. Everything is connected through gravity, through motion, through the quiet laws that shape the stars. The question of what surrounds our galaxy is, in some ways, a question about what surrounds us. The same invisible matter that holds the Milky Way together also holds the universe together. The same processes that shape the space beyond the galactic disk shaped the early cosmos. The same energy that powers the halo powers the stars inside it. Our galaxy isn't an island. It's part of a current, a pattern that stretches across everything. The darkness beyond it isn't empty. It's filled with structure, with memory, with the afterglow of ancient light. So as you listen, maybe lying there with your thoughts slowing down, you can imagine yourself drifting outward from the solar system, passing beyond the familiar constellations, beyond the thick band of the Milky Way, out through the scattered stars of the halo, and into the diffuse glow that marks the galaxy's true edge. Beyond that, the stars fade until there are only a few, and then even those disappear into the faint background of other galaxies far away. Somewhere out there, in the thin gas that fills the spaces between galaxies, the Milky Way's gravity still holds sway, a faint whisper of presence in the endless dark. That's what surrounds our galaxy. Not emptiness, but the soft continuation of everything that came before. The ghosts of other galaxies, the invisible sea of dark matter, the faint glow of hot gas, the threads of the cosmic web connecting us to everything else. It's not an edge at all, but an ongoing story, one that began long before the Milky Way formed and will continue long after it merges and transforms again, Every atom here, every breath and thought is part of that vast structure. And though we may never travel to the edge ourselves, the light from those far reaches is already travelling toward us, carrying the quiet message of where we came from and where we belong. When we talk about the Milky Way, we often imagine a flat disk of stars glowing softly in the dark, a kind of cosmic record spinning quietly through the void. That image isn't wrong, but it's also only a small part of the truth. The galaxy's shape, the structure of the thing we call home, is far more complex than the flat band we see stretching across the night sky. It isn't simply a disk, and it isn't truly still. It's a vast dynamic structure layered with motion, light, gravity, and invisible matter, surrounded by faint halos that extend far beyond what our eyes, or even our telescopes, can directly perceive. When we talk about what surrounds our galaxy, we're not talking about a simple border, but a whole hierarchy of shells, each one revealing a different aspect of its anatomy. If you could see the Milky Way from far outside, say from the vantage point of a distant galaxy, you'd see a glowing spiral with long arms curling outward like streams of light. Those arms contain most of the stars, gas and dust that give the galaxy its character. The arms themselves are not fixed structures like the spokes of a wheel. They're patterns of density, waves moving through the disk where gas compresses, stars are born and light gathers in swirls that appear almost alive. Between the arms the density drops, but even there countless smaller stars fill the gaps, creating the faint background glow that makes the Milky Way visible as a band from Earth. The disk of the Milky Way is about 100,000 light-years across, but only about 1,000 light-years thick. It's thinner than a sheet of paper compared to its width. Our solar system sits about 27,000 light-years from the galactic centre, within one of the minor spiral arms known as the Orion Arm. We're neither at the core nor at the edge, but somewhere comfortably in between, in a relatively calm and quiet region of space. From here, the galaxy stretches around us in all directions, a flattened sea of stars so vast that light from one end takes 100,000 years to reach the other. But that disk isn't perfectly flat. It's warped, bent slightly like a wave frozen in motion. The outer edges of the Milky Way curve upward and downward, an effect caused by gravitational interactions with nearby galaxies, and by the uneven distribution of dark matter in the galactic halo. If you could trace it in 3 dimensions, you'd see that it ripples like fabric, with one edge tilted above the plane and the other dipping below. The stars and gas follow that pattern, creating a subtle twist that scientists only recently confirmed through large-scale mapping surveys. It turns out our galaxy is more like a gentle spiral staircase than a flat plate. The central region of the Milky Way, the bulge, rises up from the disk like a luminous dome. It's densely packed with older stars, globular clusters, and dust clouds glowing faintly from the light of countless suns. At the very centre of that bulge lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. It's invisible to the eye, but its presence is known from the orbits of stars whipping around it at extraordinary speeds. The energy and gravity concentrated there shape the dynamics of the entire galaxy. In a way, the black hole acts like an anchor, holding the centre steady while the rest of the galaxy spins around it in a slow, graceful rotation that takes about 230 million years to complete a single turn. As we move outward from the centre, the density of stars decreases and the structures begin to blend. The bright arms give way to regions filled with gas and dust, clouds where new stars form, and gaps where radiation has cleared the space between. These regions are constantly in flux. Stars are born, live their luminous lives, and die in supernova explosions that send shock waves through the surrounding gas. Those waves trigger the birth of new stars, continuing a cycle that's been repeating for billions of years. The shape of the Milky Way isn't static, it's alive, constantly reshaped by the forces within and around it. Beyond the main disk lies something far more diffuse, the stellar halo. This is a vast, nearly spherical region of space filled with old, dim stars. Many of them are relics from the early days of the galaxy, formed before the spiral structure even existed. Others are survivors from smaller galaxies that were torn apart and absorbed by the Milky Way's gravity. These ancient stars orbit in long, looping paths, far above and below the disk, tracing the invisible skeleton of the galaxy's gravitational field. When astronomers measure their motion, they can infer the shape of that field, and in doing so, map out the distribution of dark matter that surrounds us. It's remarkable that we can understand any of this from inside the galaxy. We can't step outside and look back, but through clever observation, we've built a kind of mental image, a reconstruction pieced together from radio waves, infrared light, and stellar motion. Radio telescopes trace the faint emission of hydrogen gas, revealing the spiral structure that optical light hides behind clouds of dust. Infrared surveys see through that dust to find the stars beneath. By measuring the speed at which stars orbit the galactic centre, astronomers can determine where the mass is concentrated and where something unseen must be contributing to the gravity. Piece by piece, the invisible becomes visible, and the Milky Way's true form emerges. What that form shows us is a galaxy surrounded by an enormous halo extending hundreds of thousands of light years in every direction. This halo contains not only old stars but vast quantities of hot ionized gas. The gas is so thin that you'd never notice it if you were floating through it, but over the immense volume it fills, it adds up to a significant fraction of the galaxy's total mass. It glows faintly in X-ray light, and astronomers detect it through the way it absorbs or scatters radiation from more distant sources. It's like a faint mist surrounding the galactic disk, shaping how material flows in and out of the galaxy. That flow is critical to understanding how galaxies evolve. The Milky Way isn't a closed system. It constantly exchanges material with its surroundings. Gas falls inward from the halo, feeding star formation in the disk, while winds from supernovae and energetic stars blow material back out. This cycle keeps the galaxy alive, recycling matter over billions of years. The shape of the Milky Way isn't just defined by its stars, but by these invisible flows, the inflows and outflows of gas that connect it to the wider universe. The halo acts as both a reservoir and a shield, holding the galaxy together while allowing it to breathe. At even greater distances, the boundary between the Milky Way's halo and intergalactic space begins to blur. There's no sharp edge, no clear line separating one from the other. Instead, the density of matter gradually decreases until the galaxy's influence fades into the background of the cosmic web. In that transition zone, faint streams of gas stretch outward, linking the Milky Way to its satellite galaxies and even to its distant neighbours. These bridges of material form the faintest outlines of the network that binds the universe together. When you look at the large-scale structure of the cosmos, galaxies aren't scattered randomly. They're connected by filaments of gas and dark matter, forming clusters and superclusters that trace the skeleton of everything that exists. The Milky Way is one luminous node in that web. Understanding the shape of our galactic shell means understanding all of these layers together: the bright disk, the central bulge, the warped edges, the stellar halo, and the vast envelope of dark matter that extends even farther. Each layer tells a different part of the story. The disk is where stars are born. The bulge holds the oldest and most massive clusters. The halo carries the memory of galaxies long gone. The dark matter provides the invisible framework holding it all in place. When you add them together, you get something that isn't just a shape, but a history. A frozen record of billions of years of cosmic evolution. It's easy to forget that the galaxy we see today hasn't always looked like this. In the early universe, it would have been smaller, messier, less structured. Over time, it grew by merging with other galaxies, absorbing their stars, gas, and dark matter. Each merger left ripples in its structure, distortions in its halo, and faint traces of the galaxies that came before. Astronomers can still detect these traces in the form of stellar streams and asymmetries in the halo. It's as if the galaxy's outer shell still remembers every collision, every gravitational encounter, every moment of its long and complicated life. If we could somehow accelerate time and watch the Milky Way over billions of years, we'd see it changing shape constantly. The spiral arms would wind and unwind, stars would move in and out of the disk, and the halo would ripple like water disturbed by a passing breeze. Even the dark matter halo, though invisible, would shift as other galaxies passed nearby. The whole structure would seem alive, responding to the pull of gravity, to the birth and death of stars, to the slow, steady expansion of the universe itself. It's a reminder that nothing in the cosmos is truly still. Everything moves, everything changes, even on scales too vast for us to notice. Our understanding of this shape comes from light, from the information carried to us across unimaginable distances. Every photon from a distant star tells us something about where it came from and how it moved through space. By collecting that light, by comparing it with models and simulations, astronomers can reconstruct the three-dimensional map of the galaxy. It's a remarkable act of imagination and precision, building a picture of something we can never see from the outside, and yet, despite all our data, there's still mystery. The farther we look, the more questions arise. What exactly is the distribution of dark matter? How does the gas in the halo move? What happens at the true edge of the galaxy, where its gravity meets that of intergalactic space? Each answer leads to another layer of complexity, another pattern hidden within the larger whole. What surrounds our galaxy, then, isn't just a halo of gas or a cloud of dark matter. It's an intricate structure that reflects every interaction the Milky Way has ever had. The shells of the galaxy are like geological layers in a planet, each one preserving a record of the past. The outermost stars tell the story of mergers and collisions. The inner ones trace the steady rotation and renewal of the disk. The gas and dust connect them all, carrying material from one region to another, from one generation of stars to the next. The Milky Way shape isn't a simple outline, it's a record of time, written in light and motion. Even though we live within it, there's something strangely comforting about knowing the structure of our home galaxy. The fact that we can measure it, map it, and understand it at all is a triumph of curiosity and patience. Every image of the Milky Way, every chart of stellar motion, every simulation of its rotation, brings us closer to seeing the whole. And yet, that picture will always be incomplete. There will always be regions too faint to detect, structures too subtle to observe, layers hidden behind the glare of stars. But maybe that's part of the beauty, that even with all our instruments and knowledge, there's still mystery left at the edges. If you were to drift outward, slowly leaving the galactic disk, you'd see the light of the stars fading behind you, the spiral arms dissolving into faint streaks. You'd pass through the halo, past the old dim stars that orbit far from the centre, and into the regions where gas and dark matter dominate. Eventually you'd find yourself in the thin space between galaxies, where gravity still whispers but light grows rare. And if you looked back, you'd see the Milky Way not as a flat band, but as a glowing whirlpool suspended in the dark, surrounded by faint glows and invisible forces, a structure that is both delicate and immense. From that distance its shape would seem complete, but you'd know that even that image is only part of the truth. What defines the galaxy's shell isn't its visible light, but its reach, the extent to which its gravity and matter influence the space around it. That reach stretches farther than any star, farther than any map can fully capture. It connects the Milky Way to its smaller companions, to the faint streams of stars that orbit around it, and to the deep background of the universe beyond. The shape of our galactic shell is not a single form, but a continuum, a transition from the dense heart of the disk to the faintest whisper of influence in intergalactic space. To understand it is to understand how galaxies grow, interact, and endure. If you were to drift outward from the spiral arms of the Milky Way, leaving behind the crowded regions where stars cluster thick and bright, you'd eventually reach a realm where the light begins to thin. The familiar glow of the galactic disk fades into a dim haze, and then into almost nothing at all. The space out here is quiet, vast and seemingly empty, but it isn't truly empty. There are stars scattered across this darkness, far apart, faint, ancient. They're not part of the bustling spiral structure we call home, nor are they tethered to the dense clusters near the centre. They belong to the outer halo, the broad, diffuse region that surrounds the galaxy like a ghostly shell. These are the stars beyond the stars, the quiet remnants of a history written in gravity and time. Out here, each star is a wanderer. Most of them were not born within the Milky Way itself. They are the relics of smaller galaxies, long since devoured by our own. Over billions of years, the Milky Way has absorbed many such systems, their stars pulled apart and strewn across the halo in long, looping streams. Some of these stars orbit the galactic centre on paths so vast that a single revolution can take billions of years. To us they seem frozen, unmoving, scattered like dust. But they are part of an ongoing story, a story of growth, collision, and memory written across the sky. Astronomers call this region the stellar halo, and it's one of the most revealing parts of the galaxy. Though it contains only a tiny fraction of the Milky Way's stars, it holds the clues to how our galaxy came to be. Each of these distant suns is a kind of fossil, preserving the chemical signature of the environment in which it formed. When scientists analyse their light, they can read those signatures, much like tree rings or ancient scripts. Some of the halo's stars are incredibly metal poor, meaning they contain almost no elements heavier than hydrogen and helium. That tells us they were born when the universe was still young, before supernova had time to enrich space with new elements. These are some of the oldest stars in existence, survivors from an era when galaxies were just beginning to form. It's hard to imagine the scale of this halo. It stretches hundreds of thousands of light years from the galactic centre, far beyond the disk and the spiral arms. The density of stars out there is so low that if you placed yourself in that region, you might not see another star nearby for dozens of light years. The night sky would not be crowded like the one we see from Earth. It would be sparse, scattered, almost empty. But if you looked closely, you'd see faint threads of light tracing gentle arcs across the dark, streams of stars moving together through space, remnants of long-lost companions torn apart by gravity. These streams are among the most hauntingly beautiful structures in the galaxy. They're the remains of dwarf galaxies and globular clusters that ventured too close to the Milky Way and were gradually dismantled. Their stars, once bound together, are now stretched across the sky like trails of smoke. Some streams form elegant loops wrapping around the galaxy. Others weave and twist like ribbons caught in an invisible current. One of the most famous is the Sagittarius stream, the shredded remains of the Sagittarius dwarf galaxy, which has been merging with the Milky Way for billions of years. Its stars now form a vast arc that encircles the galaxy, evidence of an ongoing slow-motion collision happening right above our heads. The halo isn't just made of stars and streams, it's also home to globular clusters, dense spherical swarms of ancient stars bound tightly together by gravity. These clusters are among the oldest structures in the galaxy, each one containing hundreds of thousands, sometimes millions, of stars packed into a region only a few dozen light-years across. They orbit far above and below the galactic disk, tracing paths that take them through the halo and back again. Many of them formed before the Milky Way itself fully took shape. When we observe them, we're looking at pieces of the universe's earliest history still shining today. Globular clusters are like cosmic time capsules. The stars within them formed all at once, from the same cloud of gas, meaning they share similar ages and compositions. By studying them, astronomers can measure the age of the galaxy, and even the age of the universe itself. Some of these clusters are over 12 billion years old, nearly as ancient as the cosmos. They've survived collisions, mergers, and the slow tidal forces of the Milky Way's gravity. Even as smaller galaxies fell apart, these clusters endured, their stars locked together in an unbreakable gravitational embrace. They orbit the galaxy as loyal companions, tracing the same paths over and over while the universe around them continues to change. Between the clusters and the streams lies a population of isolated halo stars, wanderers with no clear origin. Some were thrown out of the galactic disk by gravitational encounters or supernova explosions. Others may have come from even farther away, flung into our galaxy by intergalactic interactions. They drift through the halo at speeds of hundreds of kilometers per second, crossing enormous distances in silence. A few of them are hypervelocity stars travelling fast enough to eventually escape the galaxy altogether. Most of these were ejected from the region near the central black hole, slingshotted outward by its immense gravity. They're cosmic exiles, carrying the story of the Milky Way's core out into the dark beyond its edges. It's strange to think that these lonely, ancient stars, scattered so far apart, still belong to the same system as the Sun. The halo may be faint and diffuse, but it's part of the same gravitational whole. If the Milky Way were a city, the halo would be its distant suburbs. Quiet, sparsely populated, but still tied to the heart of the city by invisible forces. The motions of these stars are governed by the galaxy's mass, and by tracking them, astronomers can map out that mass, including the unseen dark matter that dominates it. In that sense, these faint, forgotten stars are the galaxy's cartographers, silently tracing the shape of something we can't otherwise detect. The halo also acts as a kind of memory. Every merger, every encounter, every cosmic event leaves its signature there. When a smaller galaxy falls into the Milky Way, its stars don't vanish. They become part of the halo, their orbits preserving the shape of the path they once followed. Over billions of years, the halo becomes a layered record of these interactions, a fossilized archive of everything that's ever happened to the galaxy. By studying the motion and chemistry of halo stars, astronomers can reconstruct that history, like archaeologists uncovering ancient ruins. They can see which stars came from which galaxies, when they were absorbed, and how they shaped the Milky Way's evolution. One of the most remarkable discoveries in recent years came from the Gaia spacecraft, a European Space Agency mission mapping the positions and motions of over 1 billion stars. Gaia's data revealed patterns in the halo that had never been seen before. Streams, clumps, and shells of stars moving together, evidence of past mergers that had gone unnoticed. Among them was the signature of a massive collision about 10 billion years ago when the Milky Way absorbed a galaxy now called Gaia Enceladus, or the Sausage Galaxy, named for the elongated shape of the debris it left behind. That merger added billions of stars to the halo and reshaped the structure of the Milky Way's disk. Every star from that long-lost galaxy now orbits silently in the outer regions, a faint echo of a time when the Milky Way was still young. These discoveries remind us that galaxies are not static objects. They grow, evolve, and change through a continual process of merging and assimilation. Every star beyond the main disk is part of that process. The Milky Way's halo is a tapestry woven from the remnants of its past, each thread a stream or cluster that once belonged to another world. When you look at it in this way, the galaxy becomes less of a single entity and more of a community, a gathering of many smaller galaxies, all merged into one. The halo is where their ghosts still linger, where their light still drifts, faint but persistent, long after their original forms are gone. Even though we can't see these stars with the naked eye, their influence reaches us. The halo's gravity shapes the orbits of stars in the disk. Its dark matter defines the galaxy's rotation curve. The gas within it serves as a reservoir for future star formation. The Milky Way isn't isolated from its halo, it's connected to it in every way. The boundaries between them are soft, gradual, blurred. Material flows in and out, Stars migrate from one region to another, and over time the distinction between inside and outside becomes almost meaningless. The galaxy breathes through its halo, exchanging matter and energy with the space beyond. If you could travel out there, beyond the spiral arms, beyond the edge of the disk, you'd find yourself surrounded by this quiet population of ancient stars. They'd appear faint, reddish, and scattered, each one a tiny ember in an endless dark. Many would be hundreds of billions of years old, their light older than the Earth itself. Some would have planets, though they'd likely be barren and cold, circling suns that have long since exhausted most of their fuel. The space between them would be vast, silent, and still, broken only by the occasional glow of a passing cluster, or the distant flicker of a galaxy far beyond. It would feel lonely, but not lifeless, a place where time has stretched out so far that motion becomes imperceptible. From that vantage point, if you looked back toward the Milky Way, you'd see it as a soft, glowing spiral suspended in the void, its arms faintly illuminated against the black. You'd see the faint glow of the halo extending far beyond the bright disk, a subtle gradient fading into nothingness, and somewhere within that glow would be the faint streaks of the stellar streams, wrapping around the galaxy like ribbons of light. You'd realize that even in what seems like emptiness, there's structure, pattern, history. The stars beyond the stars are not scattered randomly. They follow the paths laid down by gravity, tracing the shape of the galaxy's invisible skeleton. The halo also connects us to something larger. The stars at its outermost edges feel not only the pull of the Milky Way, but also the gravitational influence of neighbouring galaxies, especially the Magellanic Clouds, the large and small dwarf galaxies orbiting nearby. The streams of gas and stars between them show that the halo of the Milky Way and the halos of these companions overlap. It's a reminder that galaxies are not isolated islands but overlapping systems, their edges intermingling, their histories intertwined. Even in the depths of space there's no true separation, only gradients of connection. When we think about what surrounds our galaxy, we often focus on dark matter or gas, or the vast voids between stars. But the stars in the halo are perhaps the most personal reminder of that surrounding space. They're the remnants of other worlds, survivors of collisions and transformations, still shining after billions of years. Each one is a story in itself, a survivor, a witness, a messenger from the early universe. When their light reaches us, it carries information about places and times that no longer exist. In that sense, every faint star in the halo is a piece of cosmic memory, glowing quietly in the dark, and in that glow lies a kind of continuity. The same forces that scattered these stars still shape our galaxy today. The same gravitational tides that tore apart ancient galaxies are at work even now, pulling at the Milky Way's outer edges, drawing in new companions, rearranging the stars. The halo is both the past and the future of the galaxy. It's where the Milky Way began, and where it will eventually spread when it merges with Andromeda in billions of years. The stars beyond the stars are not just remnants of history, they're the seeds of what's to come. As we drift slowly through these ideas, it's worth pausing to realize that every light in the sky, every point of brightness, is part of a much larger pattern. The stars around us are local, familiar, but beyond them lies this vast, faint population of ancient suns keeping quiet watch from afar. Their presence reminds us that the galaxy doesn't end where the light fades. It continues outward, diffuse and subtle, until it merges with the rest of the universe. What surrounds us isn't a boundary, but a continuation, a soft gradient of existence stretching endlessly outward. If you could drift out beyond the last scattered stars of the halo, beyond the old globular clusters and faint stellar streams, you'd reach a place where visible light fades almost entirely. The last of the starlight would fall behind you, and ahead there would be only the dark. not the empty kind, but the deep, weighty kind that feels full even when it looks like nothing at all. You would still be within the Milky Way's reach, though there would be almost no way to tell. Gravity would still be there, tugging softly, silent, but absolute. You'd be moving through something that can't be seen, can't be touched, and yet makes up most of what surrounds our galaxy. This invisible mass, this unseen ocean, is dark matter. The name sounds simple, but it hides one of the most profound mysteries in science. Dark matter isn't dark because it's black or shadowy. It's dark because it doesn't interact with light. It doesn't glow, it doesn't absorb, it doesn't reflect. It passes through light as if the two don't exist for each other. In fact, dark matter passes through almost everything. Through planets, through stars, through you, without leaving a trace, except for gravity. And yet, that single form of interaction is enough to shape entire galaxies, to sculpt the structure of the universe, to decide where matter gathers and where it stays empty. Without it, the Milky Way wouldn't exist at all. It's strange to think that most of the galaxy's mass, perhaps 85%, is something we've never seen. Everything we can observe, from the brightest supernova to the faintest star, adds up to only a small fraction of what's truly there. The rest is dark matter, surrounding the Milky Way in a vast invisible halo that extends hundreds of thousands of light years beyond its visible edge. It's the silent framework that holds the galaxy together, the hidden skeleton beneath the luminous skin of stars. Astronomers discovered dark matter not by seeing it, but by noticing what couldn't be explained without it. In the early 20th century, as telescopes became powerful enough to measure the motions of galaxies, scientists noticed something odd. Stars at the outer edges of galaxies were moving much faster than they should have been. According to Newton's laws, the farther a star is from the centre of a galaxy, the slower it should orbit, just as planets farther from the Sun move more slowly around it. But when astronomers measured these speeds, they didn't drop off as expected. Instead, the stars kept moving at nearly constant speeds, as if some invisible mass was keeping them tethered. That invisible mass, spread throughout and beyond each galaxy, was what we now call dark matter. It wasn't just an anomaly in one galaxy. The same pattern appeared everywhere. Whether scientists looked at spirals like the Milky Way or giant ellipticals, the stars were moving as though there was far more gravity present than the visible matter could produce. Whatever was creating that extra pull had to be invisible, abundant, and spread out in a vast halo around each galaxy. You can imagine dark matter as a kind of invisible atmosphere enveloping the Milky Way. But unlike a gas, it doesn't clump or swirl in the same way normal matter does. It's more like a smooth sea of particles that rarely interact with one another. It doesn't form stars or planets. It doesn't emit heat or light. It simply exists, shaping the motion of everything else through its gravity. That gravity is what keeps the stars in the outer reaches of the Milky Way bound to the galaxy. Without it, those stars would have drifted away long ago, flung into intergalactic space. When scientists model the Milky Way structure, they find that its visible disk, the part filled with stars and gas, sits within a much larger sphere of dark matter. This halo extends perhaps 1 million light-years in diameter, reaching halfway to the Andromeda Galaxy. It's roughly spherical, though slightly stretched by the gravitational interactions with nearby systems. It's also far more massive than the visible galaxy. If the Milky Way were a ship, the visible part would be the deck and sails, while the dark matter halo would be the ocean it floats in. Immense, invisible, and essential to keeping it stable. Despite decades of study, no one knows what dark matter actually is. We can describe what it does, how it behaves, and where it must be, but not what it's made of. The leading idea is that dark matter consists of particles, not the kind that make up atoms, but something far more elusive. These particles would have mass, meaning they create gravity, but they wouldn't interact through electromagnetism, which is why they don't emit or reflect light. They pass through ordinary matter like ghosts through walls. Physicists have proposed several possible candidates for what these particles might be. One idea involves WIMPs, weakly interacting massive particles. These hypothetical particles would have been created in vast numbers shortly after the Big Bang. They'd move slowly, cluster under gravity, and remain invisible because they barely interact with anything else. Another idea suggests axions, ultralight particles that could exist in enormous quantities, forming a kind of invisible field that fills space. There are even theories that dark matter might not be made of particles at all, but rather be a sign that our understanding of gravity itself is incomplete. For now, dark matter remains one of science's great unknowns. We can detect its influence, map its distribution, and calculate its mass, but we can't touch it or capture it. Experiments deep underground in mines and mountains have been built to try to detect it directly. These detectors are designed to pick up the faintest possible signals, the tiny jolt that would happen if a dark matter particle happened to collide with an atom. So far they've found nothing definitive. The particles, if they exist, are astonishingly good at hiding. Still, even without direct detection, the evidence for dark matter's existence is overwhelming. It isn't just galaxies that show its influence. Clusters of galaxies, the largest gravitationally bound structures in the universe, move and rotate in ways that can only be explained by enormous amounts of unseen mass. When astronomers observe how light bends as it travels through these clusters, they see patterns of distortion that match the presence of invisible matter. This effect, known as gravitational lensing, acts like a cosmic fingerprint. It lets scientists map where dark matter must be, even though it gives off no light of its own. When we look at the universe on the grandest scales, we see galaxies arranged in filaments and walls, with vast voids between them. This structure, the cosmic web, owes its shape to dark matter. After the Big Bang, tiny fluctuations in density caused dark matter to clump together first. These clumps then pulled in regular matter, gas and dust, which cooled, condensed, and formed stars and galaxies. In other words, dark matter built the scaffolding of the cosmos. Without it, the universe would have been a thin, featureless mist, with no galaxies, no stars, no planets, and no life. So, when we talk about what surrounds the Milky Way, we're not talking about something minor or decorative. We're talking about the very foundation of its existence. Every star, every planet, every molecule of gas inside the Milky Way moves within this invisible framework. Dark matter defines the galaxy's size, its rotation, even the pattern of its spiral arms. When the Milky Way eventually collides with the Andromeda Galaxy billions of years from now, it will be their dark matter halos that meet first, merging and intermingling long before the visible stars begin to collide. The idea that we are surrounded by something we cannot see is both unsettling and strangely comforting. It reminds us that the universe is still full of mystery, that there are entire realms of existence beyond our senses. The air around us is invisible too, and yet we trust in its presence because we feel its effects. Dark matter is like that on a cosmic scale, unseen, unfelt, and yet undeniably real in the way it shapes everything else. If you could somehow see dark matter, the sky would look completely different. You'd see immense ghostly structures stretching across the universe. Filaments and nodes connecting galaxies like strands in a spider's web. The Milky Way would not be an isolated spiral, but one luminous node within a much larger network of invisible mass. The dark matter halo would glow faintly around it, overlapping with those of nearby galaxies, blurring the boundaries between them. You'd see that the universe isn't mostly empty at all. It's filled with a hidden architecture of gravity, a quiet scaffolding that holds the visible world in place. It's humbling to think that everything we can see, the galaxies, stars, nebulae, planets, all of it floats in this invisible sea. Light itself moves through the currents of dark matter, bending slightly where the density changes. Even our solar system, moving through the galaxy at hundreds of kilometers per second, is drifting through a faint tide of dark matter particles that pass through us constantly, billions of them every second without leaving a trace. We live inside the ocean and never feel the water. Some scientists have suggested that dark matter may have played a role not only in the formation of galaxies but in their ongoing evolution. The way it's distributed influences how gas falls into galaxies, how stars form, and how supernovae distribute elements into space. The balance between dark matter and regular matter determines whether a galaxy forms as a graceful spiral like the Milky Way, or as a giant elliptical, smooth and featureless. Even the stability of our solar system depends indirectly on dark matter's presence, since it defines the gravitational field in which the Sun and its planets orbit. There's also a kind of poetic irony in the fact that we owe our existence to something we can't observe. All the atoms in our bodies, all the light we see, all the warmth we feel, these came into being because dark matter created the conditions for galaxies to form. The visible universe is the froth on the surface of a much deeper ocean. Every sunrise, every breath, every spark of consciousness exists only because of the silent gravity of this hidden mass. Sometimes scientists wonder whether dark matter might be more than just invisible mass, whether it might interact in ways we haven't yet imagined. Some theories propose that dark matter could form its own structures, its own kind of chemistry, perhaps even its own invisible galaxies made entirely of unseen particles. If that were true, then there could be entire universes within our universe, built of matter that doesn't interact with ours except through gravity. It's a speculative idea, but one that shows how much we still don't know. The mystery of dark matter isn't just scientific, it's existential. It challenges our sense of what reality is. For most of human history, we've defined existence through what can be seen, touched, or measured. But dark matter reminds us that most of reality lies beyond that boundary. The visible universe, beautiful as it is only the surface layer of something far greater. We are like fish swimming through a dark sea, aware only of the light reflecting off the surface above, and yet, even without seeing it, we can feel its presence in the patterns it creates. The Milky Way's rotation, the orbits of its stars, the shapes of its satellites, the distribution of galaxies across the cosmos, all of them trace the outlines of this unseen force. We may not be able to touch it, but we can map its shadow, the way wind shapes the grass even when we can't see the air itself. As the night deepens and the stars overhead seem to hang motionless in their patterns, it's worth remembering that beneath that stillness lies movement. The entire galaxy spins through the dark matter halo like a leaf carried by a slow, invisible current. The stars drift, the gas flows, the halo breathes, and through it all, dark matter holds everything together. The same unseen gravity that binds the Milky Way also connects us to the wider universe, to every galaxy, every cluster, every filament of the cosmic web. What surrounds our galaxy, then, isn't emptiness. It's this vast, invisible sea, a sea that cradles the stars, shapes their paths, and connects us to the fabric of the universe itself. We may never see it directly, but its influence is everywhere. It's in the way the Milky Way holds its form, in the way galaxies cluster together, in the way the cosmos has structure at all. If you could keep drifting outward from the halo of the Milky Way, leaving behind the last faint glimmers of stars, you'd find yourself moving into a quieter realm still. The pull of the galaxy would weaken, the density of matter would fall even lower, and for a moment it might seem as if there was nothing at all. But the universe is never truly empty. Even in the vast stretches between galaxies there is something, a thin, almost imperceptible presence. It isn't made of stars or planets, nor does it glow brightly like nebulae or supernovae. It's something softer, subtler, something that exists everywhere, yet rarely announces itself. Astronomers call it the intergalactic medium, but you could think of it as the cosmic fog, a diffuse blend of gas and dust that fills the space between galaxies, connecting everything with an invisible breath. It's hard to imagine what this fog is really like, because it defies comparison with anything we know. On Earth, fog is heavy, wet, thick enough to touch. But this cosmic fog is so thin that in a volume the size of a room, you might find fewer than a dozen atoms. It's a whisper of hydrogen and helium left over from the early universe, spread across the spaces where galaxies drift like islands on an invisible sea. You could travel through it for millions of years and never encounter anything solid. And yet, though it's unimaginably diffuse, it fills most of the universe's volume. The intergalactic medium makes up more of the universe's ordinary matter than all the stars and galaxies combined. Everything we can see, every galaxy, cluster and glowing point, is surrounded by it, suspended within its endless expanse. To see it, or rather to detect it, astronomers use indirect methods. They can't simply point a telescope at it and take a picture. Instead, they look for the way it interacts with light from distant quasars, bright, energetic sources at the centres of galaxies billions of light years away. As that light travels toward us, it passes through countless clouds of intergalactic gas. Each cloud absorbs a specific wavelength of light, leaving tiny, sharp fingerprints in the quasar's spectrum. When astronomers study these absorption lines, they can map where the gas lies and what it's made of. What they find is that the cosmic fog isn't uniform. It forms filaments, clusters, and sheets, vast, interconnected structures stretching across the universe, tracing the same cosmic web shaped by dark matter. The intergalactic medium is not just one thing either. It changes depending on where you are. Close to galaxies, it's denser, hotter, and enriched with heavier elements created by stars and supernovae. Farther away, in the emptier regions between galactic clusters, it's colder, thinner, and more pristine, made mostly of hydrogen and helium that have barely changed since the dawn of time. Scientists divide it into phases: the cool, neutral gas, the warm, ionized gas, and the hot, diffuse plasma heated by shocks and cosmic rays. These phases blend into each other gradually, forming a continuous spectrum rather than sharp boundaries. The result is a kind of cosmic weather, gentle, invisible, and constant. What's remarkable about this fog is that it doesn't just fill the void passively. It plays an active role in the life of galaxies. Gas from the intergalactic medium flows inward under the pull of gravity, feeding galaxies with the raw material needed for star formation. In return, galaxies expel matter back into the medium through supernova explosions, stellar winds, and energetic jets from black holes. This exchange keeps the cosmic ecosystem alive. It's as if galaxies breathe in and out, taking in gas from the intergalactic medium and exhaling enriched material back into it. The fog is both the womb and the grave of stars, the place where matter begins its journey into light and where it eventually returns. Around the Milky Way, the intergalactic medium blends with the outer layers of the galactic halo, forming what scientists call the circumgalactic medium. It's a transition zone between the dense, star-filled interior and the vast spaces beyond. This region contains enormous amounts of gas at temperatures of millions of degrees, hot enough to emit faint X-rays. Though we can't see it directly, its presence can be measured through the way it scatters radiation from distant sources. In a sense, our galaxy is wrapped in a warm, invisible envelope, a buffer zone between the internal world of stars and the external sea of cosmic gas. This circumgalactic medium is constantly in motion. Streams of gas fall inward, while outflows from supernovae and stellar winds push material back outward. The balance between these opposing flows determines how actively the Milky Way forms new stars. If too much gas is expelled, the galaxy's star formation slows down. If too much accumulates, new stars ignite more rapidly. The cycle is self-regulating, a feedback loop that keeps the galaxy stable over billions of years. It's one of the reasons why galaxies like the Milky Way can sustain star formation for so long, while others burn out quickly and fade into quiet ellipses. Every now and then, astronomers detect faint filaments of gas stretching between galaxies, tenuous bridges that link neighbouring systems together. These bridges are remnants of ancient interactions, traces of gas pulled out by gravity as galaxies pass near each other. Between the Milky Way and its closest companions, the large and small Magellanic Clouds, such filaments have been observed, forming a vast stream of hydrogen that arcs across the sky. It's called the Magellanic Stream, and it's a perfect example of how the cosmic fog isn't just an abstract concept but a living structure, shaped by the movements of galaxies themselves. These streams connect us to our galactic neighbours, weaving the Milky Way into the fabric of its surroundings. The idea that the space between galaxies is filled with matter might seem counterintuitive. When we look at images of the cosmos, we see galaxies shining in the dark, separated by apparent emptiness. But that darkness isn't void. It's transparent matter so diffuse that it becomes invisible. If your eyes could detect ultraviolet or X-ray light, you'd see that space is alive with faint glows and filaments. You'd see tendrils of gas connecting galaxies across millions of light years, tracing the same underlying skeleton of dark matter that gives the universe its structure. It's not empty space at all. It's a cosmic ocean of atoms drifting silently between the islands of stars. In some regions, the gas becomes dense enough to collapse under its own gravity, forming new galaxies. In others, it remains thin and quiet for eons, only occasionally disturbed by the passage of a cosmic ray or the shock wave from a distant explosion. The temperature of this gas can vary wildly, from a few thousand degrees in the cooler regions to tens of millions in the hottest. Where galaxies cluster together, their combined gravity compresses and heats the intergalactic medium until it forms vast reservoirs of X-ray emitting plasma. These regions glow faintly, invisible to our eyes but blazing in the detectors of space telescopes. Over time, the intergalactic medium has changed. In the early universe, shortly after the Big Bang, it was denser and more uniform. As the first stars and galaxies formed, their radiation began to ionize the surrounding gas, stripping electrons from atoms and turning the universe transparent. This period, known as rionization, transformed the cosmic fog from a cold, neutral gas into a warm, ionized plasma. The light of the first galaxies illuminated the fog, changing its chemistry and structure forever. Even now, that transformation continues in small ways, as radiation from stars and quasars keeps the intergalactic medium energized. The dust that drifts between galaxies adds another layer to this cosmic fog. Though it's far less abundant than gas, it plays a vital role in how light travels through the universe. Tiny grains of carbon, silicon, and metals, the remnants of ancient stars, are scattered across intergalactic space. They absorb and scatter light, dimming distant galaxies and altering their colours. When astronomers look deep into space, they have to account for this intergalactic dust, correcting their observations to reveal the true brightness of what lies beyond. The dust itself is a record of cosmic history, made from the ashes of stars that lived and died long before our galaxy was born. Every atom in this fog has a story. Most of the hydrogen and helium were forged in the first minutes after the Big Bang, when the universe was still hot and dense. Heavier elements were created later, inside stars, and spread into space through supernova explosions. Over billions of years, those elements mixed into the intergalactic medium, enriching it gradually. When new galaxies form, they draw in that enriched gas, using it to create new generations of stars and planets. The carbon in your body, the oxygen you breathe, the calcium in your bones, all of it was once part of this cosmic fog. It drifted through intergalactic space before being drawn into galaxies, stars, and finally into us. It's easy to forget that when we look up at the night sky, the light we see has travelled through this medium. Every photon that reaches your eyes has passed through countless atoms of hydrogen, through clouds of intergalactic gas, through regions of dust and plasma. The universe might appear crystal clear, but that clarity is deceptive. There's always something in between, a subtle filter that shapes the light, softens it, alters it. The cosmic fog is both barrier and bridge, something that separates galaxies but also connects them through a shared material thread. In recent years, astronomers have begun to map this fog more precisely, using networks of telescopes and advanced simulations. They've discovered that the intergalactic medium accounts for much of the so-called missing baryons, the normal matter that was predicted to exist but couldn't be found. For a long time, there was a discrepancy between the amount of matter visible in stars and galaxies and the amount predicted by cosmological models. The missing material wasn't in galaxies at all. It was floating between them, hidden in the thin, hot plasma of the intergalactic medium. By detecting faint absorption lines in the spectra of distant quasars, scientists have finally found that missing matter, confirming that the universe's inventory adds up after all. The cosmic fog is more than just the backdrop to galaxies. It's the stage on which they evolve. When galaxies form, they draw from it. When they die, they return their material to it. The fog thickens around clusters, thins between voids, and changes over cosmic time as matter flows through it. In a sense, it's the bloodstream of the universe, circulating matter and energy from one part of the cosmos to another. And though it's invisible to us, it's always there, filling every gap, every space between the lights we can see. If you were floating in this medium far from any galaxy, you wouldn't notice it at all. There would be no wind, no sensation, no sound. The temperature might be millions of degrees, but the density would be so low that there'd be no warmth. The particles would rarely collide, passing through you like ghosts. You'd be surrounded by nothing that feels like something, an invisible presence, too faint to detect directly but too important to ignore. You'd be moving through the quiet substance that holds the universe together, the forgotten matter that bridges the stars, and yet, within that quietness, everything is connected. The fog that drifts between galaxies isn't separate from us. It's the same material that once formed stars, that later formed planets, that eventually became life. The boundaries we imagine between galaxies are illusions created by distance. In reality, everything is part of one continuous medium, flowing, changing, evolving. The Milky Way is not isolated in space. It's immersed in this vast ocean of gas and dust, exchanging material with it constantly. The edge of our galaxy is not an edge at all, but a gentle blending into the wider cosmic sea. When you look at the night sky, the light from distant galaxies has passed through billions of light years of this medium. It's been bent, scattered, absorbed, and reshaped, carrying with it the imprint of everything it's encountered along the way. That light is a messenger, not just from the galaxies that emitted it, but from the universe itself, from the gas, dust, and dark matter that fill the spaces between. Every photon that reaches us is a survivor of a long journey through the fog, carrying with it a quiet record of where it's been. The next time you see an image of the Milky Way stretched across the night, remember that what surrounds it is not nothing. Beyond the glowing band of stars lies an ocean of invisible material, connecting our galaxy to every other. It's the medium through which all things move, the quiet substance that fills the universe like breath in the lungs of creation. We live inside that breath, part of it, shaped by it, and destined one day to return to it. If you could float in the space surrounding our galaxy and see beyond light itself, you'd notice that everything, every cloud of gas, every star, every wisp of dust, is threaded by something invisible. It doesn't shine, it doesn't cast a shadow, and yet it weaves through everything, binding the galaxy with silent precision. These are the magnetic fields of the Milky Way, unseen lines of force that shape the flow of matter and energy throughout the cosmos. Together they form a vast network, an invisible web that connects the smallest particles to the largest structures in the universe. Magnetism, at its heart, is one of the simplest and most familiar forces we know. We see it in the way a compass needle turns toward the north, or in the pull between two magnets on a table. Yet in space it takes on a scale so vast that our everyday experience barely prepares us for it. The galaxy's magnetic field stretches for tens of thousands of light years, coiling and twisting through clouds of gas, shaping the birth of stars and guiding charged particles along invisible pathways. It's not a uniform field, but a complex tapestry, woven from countless smaller fields generated by the motion of plasma and the rotation of the galaxy itself. The Milky Way's magnetic field is thought to be generated by a process known as a galactic dynamo. Much like the magnetic field of Earth arises from the motion of molten metal in its core, the galaxy's field comes from the motion of charged gas in its disk. As the galaxy rotates, the ionized gas, plasma, moves through existing magnetic fields, amplifying them through a process of feedback. Over time, these interactions create a large-scale field that wraps around the entire galaxy, threading through the spiral arms and extending into the halo. It's as if the galaxy has an invisible skeleton of magnetism, holding its shape and influencing its structure in subtle but powerful ways. Though we can't see magnetic fields directly, we can trace their presence through their effects. One of the clearest indicators is the polarization of light. When light passes through a region of space with a magnetic field, its electric field oscillations become aligned in a particular direction. By measuring this polarization, astronomers can map the orientation of the field lines. Radio telescopes in particular are sensitive to this effect. They detect the polarized emission from electrons spiraling around magnetic field lines, a process known as synchrotron radiation. The patterns of this radiation reveal the shape and strength of the magnetic web that runs through the Milky Way. From these observations, we know that the galaxy's magnetic field follows the spiral structure of its arms, wrapping around them in graceful arcs. The field's strength varies, but near the Sun it's around a few microgauss, billions of times weaker than a refrigerator magnet, yet enough to influence vast regions of gas spanning light years. On galactic scales, even a weak magnetic field can have enormous consequences. It affects how gas moves, how stars form, and how cosmic rays travel through space. It can shape the appearance of entire nebulae, stretching or compressing clouds of gas, and even slow the collapse of material that would otherwise form stars too quickly. Beyond the disk, the magnetic field extends into the halo, where it becomes more irregular, twisting and bending with the flow of outflowing gas and cosmic radiation. These field lines act like guide rails, channeling charged particles out of the galaxy along paths that can stretch for thousands of light years. The result is a constant, invisible flow of energy, a kind of galactic wind powered by magnetic tension and motion. This wind plays a key role in how the Milky Way interacts with its surroundings, carrying matter and magnetic flux into the intergalactic medium and helping to shape the boundaries of the galaxy itself. The magnetic web doesn't just influence matter, it also records history. When a supernova explodes, the shock waves it sends out compress and twist the surrounding magnetic fields, leaving behind patterns that persist for millions of years. As new stars form and old ones die, these local disturbances combine and overlap, creating a layered record of galactic events. Astronomers studying polarized radio emissions can see these tangled filaments and loops, reading them like pages in a cosmic diary. Each line of magnetism marks the trace of energy released long ago, still resonating through the galaxy. Even the space around our own solar system bears the imprint of this web. The Sun generates its own magnetic field, carried outward by the solar wind, forming a protective bubble known as the heliosphere. But beyond that bubble, the interstellar magnetic field takes over. The boundary between them, the heliopause, is where the solar wind and the galactic field meet and interact. Probes like Voyager 1 and Voyager 2 have crossed this boundary, measuring subtle changes in magnetic orientation that reveal the structure of the field beyond our local neighbourhood. It's a reminder that even here in our small corner of the galaxy, we're part of a much larger magnetic landscape. The interplay between magnetic fields and cosmic rays, high-energy particles moving near the speed of light, is another vital aspect of this web. Cosmic rays are constantly streaming through space, generated by supernova, black holes, and other energetic processes. As they travel, they spiral along magnetic field lines, their paths bent and guided by the field's invisible currents. This means that magnetic fields help determine how radiation moves through the galaxy, how it reaches Earth, and how it interacts with the interstellar medium. Without these magnetic pathways, the motion of cosmic rays would be chaotic and uncontrolled. Instead, the galaxy's magnetism gives their flow a kind of structure, a pattern shaped by invisible threads. In dense molecular clouds, where new stars are born, magnetic fields play an especially delicate role. As gravity pulls gas and dust together, the magnetic field resists, slowing the collapse and shaping the resulting structures. The balance between gravity and magnetism determines how many stars form, how massive they become, and even how they're distributed in clusters. Observations of star-forming regions show that the alignment of magnetic fields often matches the filaments of gas where stars are forming, as if the field lines are gently guiding the process. In this way, magnetism acts not as an opposing force but as a sculptor, shaping the raw material of creation into new systems of light and heat. Beyond the Milky Way, magnetism extends into intergalactic space, connecting galaxies through faint, enormous fields that stretch across millions of light years. These intergalactic magnetic fields are even weaker and more diffuse, but they share the same basic structure: threads and filaments woven through the cosmic web. Some scientists believe that these vast fields originated in the early universe, perhaps amplified from tiny fluctuations that arose during the Big Bang. Over time, as galaxies formed, these primordial fields were strengthened by motion, rotation, and turbulence, eventually becoming the organized patterns we see today. In this sense, magnetism is one of the oldest features of the universe, a bridge between the first moments of creation and the present-day cosmos. Though invisible, these magnetic fields can be visualized through their effects on gas and dust. In regions where dust grains align with the magnetic field, they polarize starlight passing through them. Observations from missions like Planck have mapped this polarization across the sky, revealing swirling patterns of magnetism that trace the structure of the Milky Way in fine detail. These maps show that the galaxy's magnetic field is both ordered and chaotic, smooth in some areas, tangled in others, shaped by processes that range from the calm rotation of the disk to the violent outbursts of supernovae and black holes. Near the galactic center, where the energy density is highest, the magnetic field becomes especially intense. There, massive streams of plasma flow outward, interacting with the central black hole's powerful jets. The field lines twist into towering structures that extend thousands of light years above and below the galactic plane. Observations have revealed enormous thread-like filaments in this region, glowing faintly in radio waves, evidence of magnetic activity on scales almost impossible to imagine. These structures are thought to be linked to the same processes that created the vast Fermi bubbles, the twin lobes of high-energy radiation extending from the Milky Way's core. Magnetism plays a central role in shaping those bubbles, guiding the flow of hot gas and trapping energetic particles within them. Even in the quiet outskirts of the galaxy, far from the crowded disk, the magnetic field remains. There, it interacts with the faint streams of gas that drift between galaxies, linking the Milky Way's halo to the intergalactic medium. The strength of the field weakens with distance, but its influence persists. Charged particles travelling through these regions still follow the field lines, spiralling along them like dancers following invisible steps. In this way, the magnetic web serves as a kind of galactic nervous system, transmitting information and energy across vast distances. It's easy to think of space as still, as silent, as cold. But in truth, it's full of motion. The magnetic fields that weave through it are constantly changing, twisting, and reconnecting. In plasma physics, this process is known as magnetic reconnection, when field lines break and rejoin, releasing bursts of energy. This phenomenon happens on small scales near the Sun and on vast scales in galaxies, releasing energy that can accelerate particles to incredible speeds. It's one of the ways the universe redistributes energy, balancing tension and release, order and chaos. The magnetic web is not static. It's alive, dynamic, always shifting in response to the motions of matter and the flow of time. In the quietest moments of reflection, there's something poetic, though not in the abstract sense, about knowing that magnetism touches everything. The same force that guides a compass on Earth also shapes the arms of galaxies and the flow of interstellar gas. The lines of magnetic tension that ripple through the Milky Way are connected, at least in principle, to those that span the universe. Every particle of charged matter moves under their influence. Every star forms within their reach. Even the atoms that make up our bodies were once guided by them, drawn together in the magnetic fields of long-vanished stars. To understand magnetism in space is to recognize a subtle kind of unity, a shared structure that ties all things together, visible and invisible alike. Our own galaxy's magnetic web is only one thread in a much larger fabric. Between galaxies, in the vast voids where the cosmic fog thins almost to nothing, faint magnetic fields still exist, threading the dark with structure. These fields may have been seeded by the first stars and galaxies, amplified by cosmic turbulence and shock waves. Over time, as matter gathered along the filaments of the cosmic web, magnetism followed, tracing the same patterns. In this way, the universe's magnetic structure mirrors its physical one, a grand correspondence between the seen and the unseen, between gravity's shape and magnetism's flow. If you could visualize all of this at once, the galaxies, the gas, the dark matter, and the magnetic fields, it would look like an intricate mesh of light and motion, endlessly complex but deeply coherent. Each galaxy would be a glowing node, each filament a line of connection, and through it all would run the soft hum of magnetism, binding everything into one continuous whole. The Milky Way's magnetic web is a local expression of that larger structure, a reflection of a universal pattern that stretches across the cosmos. Even now, as you sit beneath the quiet dome of the sky, you're within that web. The magnetic field of the Earth blends into that of the Sun, which in turn connects to the galaxy's larger field. The currents that flow through space pass through us too, faint but constant. Every second, streams of charged particles from distant stars pass by, guided by these invisible lines. We don't feel them, but they are always there, subtle reminders that we are part of a vast connected system extending far beyond the reach of sight. As you drift farther through the galaxy's outer regions, carried along by the faint pull of gravity and the quiet pressure of starlight, you begin to notice that the space surrounding our home isn't uniform. It isn't the same in every direction. There are pockets, cavities, and vast hollows carved into the interstellar medium, places where the density of gas and dust drops dramatically, where the stars lie farther apart and the light moves more freely. These are the galactic bubbles, enormous voids blown into the surrounding material by ancient forces, reminders that the Milky Way is not a still or passive structure, but one constantly reshaped by energy and time. The idea that our galaxy could contain bubbles on such an immense scale might sound surprising, but they are among its most common and telling features. They're born from violence, the collective force of supernovae, the winds of massive stars, or the outbursts from the galactic centre itself. When these events occur, they release enormous amounts of energy, pushing outward against the surrounding gas and dust. Over time, they carve out vast cavities that can span hundreds or even thousands of light years. The edges of these bubbles glow faintly, illuminated by compressed gas and heated by the shockwaves that formed them, while their interiors remain comparatively empty, filled only with thin, hot plasma and magnetic fields. Our own solar system happens to sit inside one of these structures, a region called the local bubble. It's an enormous cavity, about 1,000 light-years across, carved out of the interstellar medium by multiple supernova explosions that occurred over the last 10 to 15 million years. Within this bubble, the density of gas is much lower than in surrounding regions, and the temperature is much higher, reaching over 1,000,000 degrees in some areas. It's as though our part of the galaxy is suspended inside a vast invisible chamber left behind by long-dead stars. Astronomers first began to suspect the existence of the local bubble in the 1970s, when observations showed that the interstellar gas near the Sun was unusually sparse. Later, ultraviolet and X-ray studies revealed the presence of hot, diffuse plasma filling the region. Over time, detailed maps built from observations of starlight absorption and radio emission confirmed its shape and extent. It isn't a perfect sphere, more like an irregular lumpy cavity, distorted by interactions with nearby clouds of gas. The Sun isn't exactly at its centre either. It's closer to one of its inner walls, which may explain why certain directions in the sky are more transparent to distant light than others. The edges of the local bubble are where things get interesting. There, the hot, low-density interior meets cooler, denser gas from the surrounding interstellar medium, creating a boundary of compressed material. Many nearby star-forming regions, such as the Orion Complex and the Taurus molecular clouds, lie along this boundary. It's possible that the expanding walls of the bubble helped trigger their formation by compressing gas until it collapsed under its own gravity. In this way, the death of ancient stars gave rise to new ones, a kind of quiet recycling that links past and future across millions of years. Our Sun, born roughly 5 billion years ago, is too old to have been created by this particular event, but it now travels through the aftermath of other stellar deaths that shaped our local environment. The local bubble isn't unique. The Milky Way is full of similar cavities, overlapping and merging like soap bubbles in foam. Each one marks a region where massive stars once lived and died. In regions where star formation is particularly active, such as the spiral arms, bubbles can merge to form enormous superstructures called superbubbles, stretching thousands of light-years across. These regions are the engines of galactic ecology. They vent energy into the halo, mix material from different parts of the galaxy, and regulate how gas cycles in and out of star-forming zones. The result is a galaxy that breathes, expanding and contracting, inhaling and exhaling matter and energy through its countless cavities. At the largest scales, some of these bubbles reach astonishing dimensions. Towering above and below the plane of the Milky Way are two immense lobes of high-energy radiation known as the Fermi bubbles. Discovered in 2010 using NASA's Fermi Gamma Ray Space Telescope, these structures each extend about 25,000 light-years from the galactic center. They glow faintly in gamma rays and X-rays, revealing regions of energetic plasma moving at thousands of kilometers per second. No one knows exactly what created them, but there are two leading possibilities. They could be the remnants of a burst of star formation near the center, or the result of a powerful outflow from the supermassive black hole, Sagittarius A, during a more active period in the galaxy's past. Either way, the energy involved was immense, enough to carve those colossal cavities into the surrounding gas and send shockwaves rippling through the galactic halo. Even now, millions of years after the event, the Fermi bubbles remain visible, slowly fading as the hot plasma cools. Their edges mark where the expanding material meets the surrounding medium, compressing and heating it in turn. It's a pattern repeated on many scales throughout the galaxy. Energy released from stars or black holes reshapes the interstellar environment, carving bubbles and filaments that in time become the sites of new creation. Closer to home, Smaller bubbles continue to form in regions where young stars are born. Massive stars live fast and die young, spending only a few million years fusing their fuel before collapsing in supernova explosions. Before they die, their stellar winds blow away nearby gas, creating cavities that expand as the stars evolve. When they finally explode, the shock waves merge with those winds, pushing the walls outward even farther. Observations of star-forming regions show this process in action. Glowing shells of gas surrounding clusters of young stars, shimmering in infrared and radio light. These are the seeds of future bubbles, smaller echoes of the same forces that shaped our local bubble long ago. If you could see these structures in visible form, the galaxy would look far from smooth. It would resemble a kind of cosmic honeycomb. Pockets of emptiness surrounded by denser walls of gas, threaded with filaments of magnetic field and dust. Each bubble would tell a story, of stars born, of energy released, of matter moved and transformed. Over time they merge, collapse and reform, erasing old boundaries and creating new ones. The Milky Way's shape, its texture, even the distribution of its stars is partly the result of this constant cycle of expansion and renewal. Inside the local bubble, our solar system moves through a relatively calm environment, protected by the sun's magnetic field and the solar wind. The thin gas that fills the bubble produces only faint traces of absorption in starlight, which is why the night sky appears so clear in most directions. In a sense, we owe our view of the universe to the bubble we inhabit. If we were embedded in a denser region of gas and dust, the light from distant stars and galaxies would be dimmed and scattered, obscured by the haze of the interstellar medium. Instead, we have a window, a region of clarity that allows us to see far beyond our own neighbourhood. The sun's journey through this cavity is not eternal. It moves through the galaxy at about 200 kilometers per second, orbiting the centre once every 230 million years. Over time, it will drift out of the local bubble and into another region of the interstellar medium. In fact, it may already be approaching a denser cloud known as the local interstellar cloud, a small warm region embedded within the larger cavity. As the solar system passes through different environments, the balance between the solar wind and the surrounding gas changes, slightly altering the size and shape of the heliosphere, the protective bubble of plasma that surrounds us. These interactions happen slowly, over tens of thousands of years, but they remind us that even here, in this quiet corner of space, we're always moving through a dynamic, evolving landscape. The study of these bubbles has revealed much about how galaxies maintain balance. They act as pressure valves, releasing the energy built up from star formation and preventing the interstellar medium from collapsing too quickly. Without them, gas would clump together more easily, forming stars at an unsustainable rate. Instead, the outflows from bubbles redistribute that gas, heating some regions while cooling others, creating the diversity of conditions needed for different kinds of stars to form. In this way, destruction and creation are not opposites, but partners. One feeds the other, ensuring the galaxy's longevity. When astronomers map the Milky Way in radio and X-ray light, they see these structures everywhere. Some are fresh and bright, others old and fading. Together they form a record of the galaxy's most energetic moments. By studying the size, shape and distribution of bubbles, scientists can infer the history of star formation in different regions. In the spiral arms, where massive stars are born in abundance, bubbles are numerous and often overlap. In the quieter interarm regions, they're rarer and smaller, the remnants of isolated events. The pattern is like a fingerprint, unique to each part of the galaxy, yet following the same basic rules of physics everywhere. Beyond the physical details, there's something deeply human about the idea that we live inside the remnant of long-extinguished stars. The atoms that make up our world, the carbon, oxygen and iron in our bodies and our planet, were created in the hearts of massive stars that ended their lives in explosions, much like those that carved the local bubble. We are literally surrounded by the evidence of our own origins. The same forces that cleared the space around us also seeded it with the materials necessary for life. When we look up at the night sky, we're gazing through a window created by those ancient deaths, through the walls of a bubble that carries the memory of violence turned into stillness. These bubbles are more than empty cavities. They're boundaries between different phases of the interstellar medium. Inside, the gas is hot and ionized. Outside, it's cooler and denser. The interactions at those boundaries are complex and beautiful. Magnetic fields drape across the surfaces, cosmic rays pass through, and thin layers of plasma ripple where the two regions meet. Some scientists compare them to membranes, separating different parts of the galaxy's ecosystem, while still allowing the exchange of matter and energy. Across these membranes, information passes in the form of radiation and magnetic disturbances, linking distant parts of the galaxy through subtle physical connections. On an even larger scale, the Fermi bubbles hint that the entire Milky Way may once have gone through periods of greater activity. The energy required to create them suggests that the central black hole was not always as quiet as it is now. Perhaps millions of years ago, it consumed a large amount of gas, generating powerful jets and winds that blew material out of the galactic centre. The echoes of that event still linger, not just in gamma rays, but in the magnetic and structural changes imprinted on the surrounding space. It's possible that these outbursts occur cyclically, shaping the galaxy in waves of expansion and cooling that repeat across eons. Even now, smaller bubbles continue to form, not just from supernovae, but from collective processes like stellar winds and turbulence. They're part of the galaxy's living system, reminders that no region of space is static for long. Over billions of years, the Milky Way has been sculpted by these forces into the shape we see today. A disk threaded with filaments, surrounded by a halo of diffuse gas, marked by the scars of countless explosions that have come and gone. The bubbles may fade, their edges may dissolve, but their influence remains in the structure of the interstellar medium, in the distribution of stars, in the very texture of the galaxy itself. As you imagine these enormous cavities, some surrounding you, others stretching above and below the galactic plane, it becomes easier to see the Milky Way not as a single object but as a living system, full of motion, feedback and transformation. The bubbles are its lungs, its breathing spaces, its pauses between bursts of creation. Through them, energy circulates, matter recycles, and the galaxy renews itself again and again. And in the midst of it all, here we are, drifting quietly through one of those ancient hollows, sheltered within the aftermath of stellar fire. When we picture a galaxy, it's easy to imagine it as a peaceful, solitary system gliding through space, its stars orbiting in serene balance. The Milky Way can feel that way from here, calm, steady, dependable. But the truth is that galaxies are restless things. They move, they pull, they collide, and the space surrounding our galaxy is full of the remnants of those encounters. The calm we see today is not the calm of stillness, but of aftermath. It's the silence left behind after immense slow-motion collisions that unfolded over billions of years, leaving faint traces behind. The echoes of collisions that continue to shape the Milky Way even now. The Milky Way's outer regions are full of these echoes. They appear as long, thin streams of stars arcing across the sky, as irregular clusters in the halo, and as subtle distortions in the motion of stars near the edge of the disk. Each one is a piece of history, the remnant of a smaller galaxy or star cluster that once passed too close and was torn apart by the Milky Way's gravity. These events are not rare accidents. They're the very process by which galaxies grow. The Milky Way, like most large galaxies, was built through mergers by consuming smaller companions over cosmic time. Every star that orbits in the halo, every faint stream winding through the outskirts, is a relic of that long process. You can think of these collisions not as violent impacts but as long dances. When two galaxies meet, They don't crash head-on like solid objects. Their stars are separated by such vast distances that they almost never collide directly. Instead, gravity does the work. As the galaxies draw near, their mutual attraction pulls and stretches them, distorting their shapes, sending tidal forces rippling through their structures. Stars and gas clouds are pulled out into long tails and loops. Some are flung outward into intergalactic space. Others fall inward, mixing into the larger galaxy. Over time, the smaller system is absorbed completely, leaving behind a stream of stars tracing its final orbit, a glowing signature of its passage. One of the most striking of these features in our own galaxy is the Sagittarius Stream. It's the remnant of the Sagittarius dwarf spheroidal galaxy, a small companion that has been merging with the Milky Way for billions of years. As it orbits, the Milky Way's gravity pulls it apart, stripping stars from its outer regions and stretching them into a vast arc that wraps nearly halfway around the galaxy. When astronomers map this stream, they can see its path tracing a ribbon through the halo, looping over and under the galactic plane. Each star in that stream is a piece of a galaxy being slowly unmade, moving in near-perfect memory of its original trajectory. The Sagittarius dwarf is still there, or at least what's left of it. Its core remains intact, a faint, elongated object orbiting through the outer regions of the Milky Way. But it's shrinking with every pass, losing more material to the larger galaxy's pull. In time, it will be gone entirely, its stars dispersed into the halo, indistinguishable from the rest. Yet even when it's gone, its trail will remain, a long curve of stars marking where it once moved. Astronomers can use these stellar streams like cosmic seismographs, reading the ripples of gravity they trace to learn about the Milky Way's invisible mass, especially its dark matter halo. Each stream follows a path carved by gravity, and the way that path bends and twists reveals the shape of the unseen matter surrounding us. The Milky Way has absorbed many such systems. The halo is full of them, faint ghost-like streams and overdensities named for the regions where they were first found. The Helmi Stream, the Orphan Stream, the Cetus Polar Stream, the Gaia-Enceladus Sausage Merger. Each tells a story of an ancient encounter. The Gaia-Enceladus event in particular was one of the most significant. Roughly 10 billion years ago, when the Milky Way was still forming, it collided with a galaxy nearly half its own size. The merger reshaped both systems, scattering billions of stars into the halo and altering the structure of the galactic disk. The remnants of that collision are still visible today, not as a single stream, but as a vast, elongated population of stars moving in distinct orbits, their composition and motion marking them as immigrants from another world. These mergers didn't happen all at once, and they didn't stop long ago. They're ongoing. Even now, the Milky Way continues to interact with its smaller companions, the dwarf galaxies that orbit nearby. Some of them are already being drawn in, their outer stars stripped away and incorporated into our halo. The Large and Small Magellanic Clouds, two of the brightest satellite galaxies visible from Earth's southern hemisphere, are bound to the Milky Way, and on paths that will eventually lead to their assimilation. The gas trailing behind them, the Magellanic Stream, stretches for hundreds of thousands of light years, a bridge of hydrogen connecting them to our galaxy. This stream, along with the faint stellar bridges that may accompany it, is another echo of interaction, a sign that the process of galactic merging is still unfolding. When you think about the timescales involved, it's almost impossible to imagine. The stars in these streams move at hundreds of kilometers per second, yet their orbits take hundreds of millions of years to complete. The entire process of merging from first approach to final absorption can last billions of years. If you could watch it in fast motion, galaxies would look less like rigid disks and more like fluid forms, flowing into each other, rippling, merging, and reforming. The edges blur, the centers swell, and new patterns emerge. It's less an act of destruction than one of transformation. The Milky Way as we see it today is the cumulative result of countless such transformations, each one leaving subtle marks that astronomers are still uncovering. The evidence of these events isn't limited to the halo. The disk of the Milky Way itself shows signs of disturbance, waves and ripples in the distribution of stars that suggest past interactions. Some of these may have been caused by smaller galaxies passing nearby, tugging at the disk as they went. The Sagittarius dwarf, for instance, may have triggered waves of star formation and gravitational oscillations as it plunged through the galactic plane. These ripples move through the disk like waves on a pond, gradually dissipating but leaving patterns that can still be measured. Even here, in the region where our Sun orbits, the positions and velocities of stars bear faint traces of these interactions, subtle motions that tell of long-past encounters. When scientists analyse these patterns using data from the Gaia spacecraft, they find that the Milky Way's disk is not perfectly flat or smooth. It's warped and vibrating, as though still ringing from impacts millions of years old. Each ripple carries information about when and how a smaller system passed through. By modelling these motions, astronomers can reconstruct a timeline of past collisions, turning the Milky Way into a kind of living record of cosmic history. The stars are the archive, and their motions are the writing. The halo itself is full of such writing. The orbits of halo stars are far more varied than those in the disk. Some move in elongated loops, some in tilted orbits, some even backwards relative to the disk's rotation. These motions are clues to their origins, signatures of the galaxies they came from. Stars born within the Milky Way tend to move in orderly patterns, following the rotation of the disk. Those accreted from elsewhere move in more chaotic ways, their orbits shaped by the paths of their parent systems. When astronomers map the distribution of these orbits, they can see distinct clumps, each representing a different ancestral galaxy now long gone. Even the chemical composition of stars tells part of this story. Stars formed in different galaxies have distinct chemical fingerprints, reflecting the conditions of their birth. By measuring the abundance of elements like iron, magnesium and nickel, scientists can tell which stars were born in the Milky Way and which came from mergers. The halo contains many metal-poor stars, old, simple stars that formed early in the universe's history, often in smaller galaxies that had not yet undergone much chemical enrichment. Each one is a relic from a time before the Milky Way existed in its current form. Together they make up a mosaic of origins, a collection of stories written in starlight. It's remarkable to think that all of this motion, all of these collisions and mergers, happens without sound or flash. There's no explosion when galaxies collide, no audible impact. The stars simply pass through each other's gravitational fields, their paths bending and reshaping slowly. The light from those stars, though, carries the memory. It moves through space as a quiet record of everything that's happened, eventually reaching us after tens of thousands or millions of years, allowing us to piece together a story that would otherwise be invisible. Even our galaxy's future is written in this same language of motion and gravity. In about 4 billion years, the Milky Way will begin to merge with the Andromeda Galaxy, our nearest large neighbour. The two are already moving toward each other, drawn by their mutual gravity at a speed of roughly 110 kilometers per second. When they finally meet, their dark matter halos will merge first, followed by their disks and stars. From a distance, the encounter will look slow and graceful. Two spirals entwining, stretching and blending into one another. Over the following billions of years, their shapes will change, their stars will settle into new orbits, and a new, larger galaxy will form, likely an elliptical, glowing softly with the combined light of both. The Sun, if it still exists then, will move through this new structure, orbiting in the merged remnant of two once separate systems. What surrounds that future galaxy will be the same as what surrounds ours now: dark matter, gas, and the faint remnants of the collisions that made it. When we look at images of distant galaxies caught in the act of merging, their arms twisted and stretched, their cores glowing with bursts of star formation. We're seeing what our own galaxy has experienced and will experience again. Those luminous bridges of stars, those long tails of gas stretching into space, are the echoes of the same process that built the Milky Way. The universe is full of these encounters. Every large galaxy we see today is the result of hundreds or thousands of mergers, each one adding new material, new stars, new structure. The space around them, the halos and streams and filaments, are the fossils of those events, preserved in the slow motions of ancient stars. There's something profound about realizing that we live inside one of these stories, that the sky above us, the stars we see each night, are part of a structure forged by endless interaction. The halo surrounding our galaxy isn't a still border. It's the record of motion, of absorption, of change. Each faint star out there is a witness to a collision so slow that it takes billions of years to complete, yet so powerful that it reshapes the very structure of a galaxy. Even now, as you read this, those processes continue. The Milky Way's gravity is tugging gently on its companions. The Sagittarius dwarf is still being stripped. The Magellanic Cloud still sends streams of gas trailing behind them. The halo still ripples from encounters long past. The galaxy never stops changing, never stops remembering. If you could step outside the Milky Way and look back, you'd see these echoes all around it. Faint arcs of light looping through the halo, delicate streams winding outward, clouds of gas stretched thin across the darkness. They'd look fragile, like threads of silk suspended in air. But they're the scaffolding of the galaxy's history. Each one traces the gravitational path of something that once was, a smaller system that gave itself to the larger whole. The galaxy's shape, its balance, its very existence as a stable spiral depend on those mergers. Without them, it would have been smaller, simpler, less structured. The beauty we see now, the spiral arms, the glowing disk, the rich halo, is the product of billions of years of quiet collisions. The echoes of those events reach us not just as patterns in space, but as the light of individual stars. Every star that shines in the night sky carries within it the story of its origin. Some were born here, in clouds of gas nurtured by the Milky Way. Others began life in other galaxies, far away and long ago, and now orbit quietly as part of ours. The light from those stars mingles together, indistinguishable, as if to remind us that identity in the universe is never permanent, that everything changes, merges, and becomes something new. As we drift farther outward, beyond the bright lanes of the Milky Way's spiral arms, and into the faint halo of stars and gas that surrounds it, the darkness begins to fill again with light. Not the light of distant galaxies scattered across the sky, but the light of something closer, something that moves with us. Two soft glows hang near the southern horizon, faint and cloud-like, visible even to the naked eye on a clear night far from city lights. They've been known since ancient times, guiding travellers and inspiring stories long before anyone understood what they were. Today we call them the Magellanic Clouds, the large and small Magellanic Clouds, and they are our closest galactic neighbours, silent companions drifting through space alongside the Milky Way. From Earth, they appear as pale smudges, ghostly and serene, each about the size of a hand's width against the night. The large Magellanic Cloud lies about 160,000 light-years away, while the small Magellanic Cloud is slightly farther, around 200,000 light-years distant. To the unaided eye, they look like patches of fog, but through a telescope they reveal themselves as galaxies in their own right. Clusters of stars, clouds of gas, and traces of dust glowing faintly in the dark. They are dwarf galaxies, smaller and less structured than the Milky Way, yet complex in their own ways. Each one contains billions of stars, many newly formed, others ancient and dim. Together they orbit the Milky Way, bound to it by gravity, moving in slow, looping paths that have lasted for billions of years. For centuries, the nature of these clouds was a mystery. To early observers, they seemed like peculiar patches of faint starlight, part of the Milky Way but somehow detached from it. It wasn't until the early 20th century that astronomers realized they were separate galaxies, each with its own population of stars and its own internal structure. Their names come from Ferdinand Magellan, whose expedition in the 16th century recorded them during its voyage around the world. But the knowledge of them is far older. They appear in the records and stories of many cultures in the southern hemisphere, a familiar and constant presence in the sky long before telescopes or modern astronomy existed. The Large Magellanic Cloud, or LMC, is the larger of the two, spanning about 14,000 light-years across. It's a barred irregular galaxy, meaning it doesn't have the clear spiral shape of the Milky Way, but instead a more uneven structure, with bright knots of star formation scattered throughout. One of the most striking regions in the LMC is the Tranquil Nebula, a vast cloud of gas and dust that glows brightly with the light of newly born stars. It's one of the most active star-forming regions in the entire local group of galaxies, and if it were as close to us as the Orion Nebula, it would cast shadows on the ground. Within it lies a massive star cluster called R136, containing some of the most massive and luminous stars known, stars hundreds of times the mass of the Sun, shining millions of times brighter, living brief, brilliant lives before ending in supernovae that send waves of energy rippling through the surrounding gas. The Small Magellanic Cloud, or SMC, is smaller, more irregular, and more distorted, measuring only about 7,000 light-years across. Its shape has been stretched and twisted by the gravitational pull of both the LMC and the Milky Way. It contains fewer heavy elements than its larger companion, meaning its stars are generally older and less chemically enriched. Yet it too is forming new stars, particularly in the regions where tidal forces have compressed its gas. The SMC and LMC are connected by a bridge of material known as the Magellanic Bridge, a stream of hydrogen gas that stretches between them, filled with young stars that likely formed as the two galaxies interacted. This bridge is one of the clearest signs that they are not isolated systems, but parts of a larger, shared dynamic with the Milky Way. Trailing behind both galaxies is another feature, even grander in scale, the Magellanic Stream. This immense ribbon of hydrogen gas extends for more than 600,000 light-years, wrapping around the Milky Way like a vast flowing tail. It was torn from the Magellanic Clouds by the Milky Way's gravity and by the pressure of the hot gas that fills the galactic halo. The stream is invisible to the naked eye, but radio telescopes can detect its faint emission, tracing its path across the sky. It's one of the most spectacular examples of how galaxies interact, how gas can be stripped, stretched, and reshaped by gravitational tides, forming bridges and tails that link neighbouring systems together. The origins of the Magellanic Stream are still being studied. Some models suggest it formed gradually over billions of years as the Magellanic Clouds orbited the Milky Way, losing gas with each pass. Others propose a more dramatic origin, perhaps from a close encounter between the two clouds themselves that pulled material out through tidal forces. Whatever the exact cause, the result is a living connection, a tangible gaseous thread that ties our galaxy to its companions. It's a reminder that space, even on this immense scale, isn't a vacuum, but a medium in constant motion, where galaxies trade material and energy like ocean currents mingling across invisible borders. The Magellanic Clouds are not the only companions of the Milky Way, but they are the most visible and the most massive. Dozens of smaller dwarf galaxies orbit farther out, many so faint they were discovered only in recent years. Some, like the Sagittarius dwarf or the Sculptor dwarf, are already being torn apart, their stars added to the Milky Way's halo. Others remain intact, tiny islands of light on the edge of our gravitational domain. Together they form a family, a system of satellites bound to our galaxy, each following its own path, each contributing to the Milky Way's slow evolution. The Magellanic Clouds are simply the brightest members of that family, their presence a quiet testament to the interconnectedness of everything that drifts in this part of the universe. If you could step outside the galaxy and look back, you'd see the Magellanic Clouds as two bright companions trailing just beyond the Milky Way's luminous disk. Their orbits would form graceful arcs, looping around the galaxy's centre. Between them and the Milky Way, you'd see the faint glimmer of the Magellanic Stream, a bridge of gas illuminated by the soft glow of the cosmic background. Beyond them, scattered across the dark, would be the other dwarf galaxies of the local group. Faint, small, but real, each one moving under the influence of the Milky Way's massive halo. Together, these systems form a dynamic, gravitationally bound ensemble that slowly evolves as time passes. The Milky Way isn't a lone traveller through space, it's the hub of a small cosmic cluster surrounded by these drifting companions. The interactions between the Milky Way and the Magellanic Clouds have left marks on both. The tidal forces pulling on the clouds have distorted their shapes, while the gas they've lost to the Milky Way may have fueled star formation in our galaxy's outskirts. Some of the material stripped from them may even be falling toward the Milky Way's disk now, feeding it with fresh hydrogen that will become the raw material for future generations of stars. The relationship is not one-sided. Just as the Milky Way shapes the Magellanic Clouds, they in turn shape the Milky Way, subtly but persistently, through gravity and motion and the exchange of matter. When astronomers simulate this system in computers, they find that the orbits of the Magellanic Clouds are not simple circles, but long looping trajectories that may be evolving over time. It's possible that the clouds are not long-term satellites at all, but recent arrivals, galaxies that fell into the Milky Way's gravitational influence only a few billion years ago. If that's true, then what we're seeing now may be the early stages of their eventual merger with our galaxy, a process that will unfold slowly over the next several billion years. As they spiral closer, their gas will continue to be stripped away, their stars will disperse into the halo, and their individual identities will fade, absorbed into the larger whole. There's a strange beauty in that inevitability. Every galaxy we see is both itself and the sum of everything it has absorbed. The Milky Way once consumed others, and someday it will consume these too, folding their light into its own. Yet even after they're gone, the memory of them will remain, written in the streams and clouds of gas that circle the galactic halo. The Magellanic Clouds are living examples of that ongoing story, not relics of the past, but participants in a process that has been shaping the cosmos since the first galaxies formed. Beyond their scientific importance, there's something quietly humbling about their presence in the sky. For those who live in the southern hemisphere, they are among the most reliable features of the night, shining softly year-round, unchanging to the eye even as the Earth turns and centuries pass. They remind us that the galaxy we live in isn't alone, that it moves through space accompanied by others, bound by gravity and time. The stars within those clouds shine with their own histories, their own cycles of birth and death, their own planetary systems perhaps. And yet, through the long reach of gravity, their fate is tied to ours. In a way, the Magellanic Clouds serve as a bridge between the personal and the cosmic. They're near enough to feel familiar, part of the same celestial landscape that holds our own stars, yet distant enough to represent the scale of the universe's architecture. Their faint glow connects our nightly sky to the structure of the local group, to the motion of galaxies across millions of light years, to the shared dance of all matter under gravity. Every time light from those distant stars reaches Earth, it crosses the invisible boundary between galaxies, carrying with it the quiet signature of connection. If you could travel there to the large Magellanic Cloud, you'd find yourself in a galaxy smaller and calmer than ours, but alive with activity. The sky would glow with the light of nearby nebulae, vast clouds of ionized gas lit by newborn stars. You might see clusters of blue giants scattered like embers across the heavens, their light reflecting off surrounding dust. The Milky Way itself would dominate one part of the sky, an enormous spiral shining with the combined light of hundreds of billions of stars stretching from horizon to horizon. It would be both familiar and foreign, the same galaxy we know, but seen from outside, surrounded by the quiet company of its satellites. In the small Magellanic Cloud, the view would be similar but fainter. The stars would appear sparse, the clusters older, the gas clouds dimmer. Yet even there, you'd sense the connection to the larger whole. The same gravitational pull that keeps the SMC bound to the LMC and to the Milky Way would be visible in the slow drift of its stars, in the faint arc of the bridge of gas connecting it to its larger companion. You could follow that bridge in your mind's eye, tracing it across tens of thousands of light years, through the empty darkness where no stars shine, and into the bright body of the neighbouring galaxy. From there, your thoughts could stretch farther still, following the Magellanic Stream as it curves around the Milky Way and fades into the halo. You'd realise then that what surrounds our galaxy isn't emptiness, but motion, a continuous exchange of matter and light across unimaginable distances. The Magellanic Clouds also help astronomers study the physics of galaxy formation and interaction. Because they're so close, they offer a unique opportunity to observe these processes in detail. We can study their stars individually, measure their chemical compositions, and trace the dynamics of their gas. In doing so, we learn not only about them, but about how all galaxies evolve. Their tidal bridges and streams provide real examples of how gravity sculpts matter on galactic scales. Their clusters of young stars show us how star formation proceeds under different conditions. Their interactions with the Milky Way reveal how galaxies exchange gas, and how that gas fuels the cycles of creation within each system. The Magellanic Clouds may be small, but they carry lessons that extend across the universe. In their quiet orbits, in their drawn-out tails of gas, in their shared gravitational bond with the Milky Way, they show that galaxies are not independent objects, but connected parts of a greater structure. Every movement, every exchange, every stream of material is part of that connection. The cosmos doesn't build walls between its components, it builds bridges, and as you hold that image, the Milky Way with its two luminous companions, the arcs of gas that link them, the faint streams that wrap around them like threads, the sense of continuity deepens. Everything that surrounds our galaxy is part of that network, from the dark matter halo that anchors it to the faintest wisp of gas drifting in its outskirts. The Magellanic Clouds are our companions, not just in proximity, but in motion, in evolution, in fate. They are moving with us through time toward whatever comes next, a future where they too will merge with the Milky Way, becoming part of its light, its structure, its story. Beyond the Magellanic Clouds, farther out than the bright clusters of stars that still share their light with the Milky Way, there is a quieter realm. It's a region where galaxies grow small, where light begins to thin, and where gravity's hold stretches to its faintest limits. Out there, orbiting in near silence, are dozens of faint companions, the satellite galaxies of the Milky Way. They are our galaxy's smallest neighbours, its oldest witnesses, and its most delicate structures. They drift through the halo like sparks caught in the slow wind of time, invisible to the eye but essential to the story of what surrounds us. The satellites of the Milky Way are often described as dwarf galaxies, but that term only hints at their diversity. Some contain only a few thousand stars, while others hold millions. Some are compact and dense, while others are diffuse and ghostly, barely distinguishable from the background of the sky. A few, like the Magellanic Clouds, are still active, rich with gas and forming new stars. Most, though, are ancient and quiescent, their gas long gone, their stars dim with age. They are the remnants of the galaxy-building process, the small systems that survived the turbulent early universe and now orbit within the Milky Way's gravitational domain. The first of these faint companions were discovered more than a century ago, The Sculptor and Fornax dwarves were identified in the 1930s, small collections of stars moving together near the southern constellations that bear their names. Over the decades that followed, more were found: Draco, Ursa Minor, Carina, Sextans, Laocoön, and Tu. Each new discovery revealed another fragment of the Milky Way's outer structure, another piece of its extended family. Then, in the 21st century, as telescopes became more sensitive and sky surveys more detailed, the number of known satellites multiplied. Instruments like the Sloan Digital Sky Survey and the Dark Energy Survey uncovered a hidden population of ultra-faint dwarfs, so dim that they contain fewer stars than some globular clusters. Dozens of these tiny galaxies have now been catalogued, and more are likely waiting to be found. Each one is unique. Some are relatively nearby, only a few tens of thousands of light-years from the Milky Way centre. Others orbit much farther out, at distances of several 100,000 light-years, near the edge of the galaxy's dark matter halo. Together, they form a complex, layered system that extends far beyond the visible disk of the Milky Way. From a distance, they would look like a faint, uneven halo of light surrounding the galaxy, a cloud of tiny companions following it through space. The orbits of these satellites are varied and complex. Some move in elongated paths that bring them close to the Milky Way before carrying them far out again. Others travel in nearly circular orbits, remaining at roughly the same distance for billions of years. Their motions are influenced not only by the Milky Way's gravity, but also by one another's, as well as by the distribution of dark matter in the galactic halo. The system as a whole is dynamic, constantly evolving. Some satellites are being pulled apart by tidal forces, leaving behind streams of stars that stretch across the sky. Others may eventually merge completely, adding their stars to the Milky Way's halo just as countless others have done before. These satellites are not just ornaments, they are fundamental to understanding how galaxies form and grow. In the framework of modern cosmology, large galaxies like the Milky Way are built hierarchically, from the merger and accretion of smaller systems. The satellites we see today are survivors of that process, the few that escaped complete assimilation. Their stars preserve the conditions of the early universe, and their motions trace the structure of the Milky Way's dark matter halo. By studying them, astronomers can probe both the galaxy's history and the nature of the invisible matter that surrounds it. The smallest of these galaxies are sometimes called ultra-faint dwarfs. They are among the most ancient and primitive objects known, fossils from the first generations of galaxy formation. Many contain stars that formed more than 12 billion years ago, before the Milky Way itself had fully assembled. These stars are extremely metal-poor, composed mostly of hydrogen and helium, with only trace amounts of heavier elements. They represent the early stages of chemical evolution, when the universe had not yet been enriched by successive generations of stars. In a sense, these tiny galaxies are like time capsules, preserving the conditions of the cosmos when it was still young. Despite their small size, the satellite galaxies are rich in information. The distribution around the Milky Way provides clues to how the galaxy's dark matter halo is shaped. Early theories predicted that satellites would be scattered randomly, but observations suggest something different. Many of them lie in a rough plane, a vast thin sheet encircling the Milky Way at an angle to its disk. The reason for this alignment is still debated. Some scientists think it may be the result of past mergers, perhaps the remnants of a single, larger system that was broken apart long ago. Others propose that it could reflect the structure of the cosmic web, with the satellites entering the Milky Way's halo along the same filament of dark matter. Whatever the cause, it's a reminder that even in what seemed like chaos, there are patterns, subtle, long-lasting structures that persist across billions of years. The relationship between the Milky Way and its satellites is not static. Gravity is constantly reshaping it. As the satellites orbit, the Milky Way's pull distorts them, stripping stars and gas from their outer regions. Some of these stars form tidal streams, long arcs of light that stretch across the sky. The Sagittarius stream is one such example, a ribbon of stars that winds around the galaxy, marking where the Sagittarius dwarf galaxy has been slowly dismantled. Other streams, too faint to see without deep imaging, crisscross the halo, evidence of past accretions. Each one is a thread in the tapestry of the Milky Way's growth, woven from the remnants of its smaller companions. The satellites also help sustain the Milky Way's life cycle in a quieter way. Some carry reservoirs of hydrogen gas, which can be drawn inward over time, feeding star formation in the outer disk. Others, already stripped of their gas, contribute through their stars, enriching the halo with heavier elements as those stars age and die. Even when they are no longer visible as distinct systems, their material continues to circulate through the galaxy, recycled into new generations of stars and planets. In this sense, the satellites are not merely passive companions, but active participants in the galaxy's evolution. It's easy to imagine these dwarf galaxies as lonely, isolated things, but they are not as solitary as they seem. Many of them move in groups, bound together by their own mutual gravity, even as they orbit the Milky Way. The Magellanic Clouds, for instance, are a binary pair, two galaxies orbiting each other while both circle our own. Some of the smaller dwarfs may be satellites of the Magellanic Clouds themselves, forming a hierarchy of systems nested within systems. This layered structure mirrors the larger architecture of the universe, where galaxies cluster together in groups and clusters, all linked by the web of dark matter that spans the cosmos. The faintest of these galaxies challenge the limits of observation. Some are so diffuse that they were only discovered through the collective light of their stars, detected statistically in surveys rather than visually. Others were found because their stars moved together, revealing their shared motion against the background of the sky. As technology improves, astronomers expect to find many more. The next generation of telescopes, like the Vera C. Rubin Observatory, will map the sky in unprecedented detail, revealing faint structures that have so far remained hidden. Each new discovery will add another piece to the puzzle, refining our understanding of how galaxies like the Milky Way grow. The story of the satellites is not only about structure and formation, but about endurance. These tiny galaxies have survived for billions of years despite the overwhelming gravity of their host. Some have passed close to the Milky Way multiple times, enduring repeated tidal stresses that would have torn lesser systems apart. Their survival speaks to the strength of their dark matter halos, which hold them together even as their stars are stripped away. In that sense, they are living proof of dark matter's role in shaping the cosmos. Without it, these fragile systems could not exist. If you could travel to one of these dwarf galaxies, it would look very different from our home. The stars would be sparse, scattered across the sky with wide gaps of darkness between them. There would be no bright band of a Milky Way overhead, only the faint hazy glow of our galaxy seen from afar, stretching like a luminous arch across the black. It would dominate the view, enormous and soft, the light of hundreds of billions of stars seen as a single structure. You'd see the spiral arms faintly outlined, the core glowing with concentrated light, the halo extending outward into a diffuse blur. You'd be able to trace, just barely, the faint lines of the Magellanic Stream curving through the dark, connecting your tiny galaxy to the great one that pulls it along. It would be a beautiful and humbling sight, the experience of seeing home from the outside. From that vantage point, the relationship between the Milky Way and its satellites would become clear. You'd see them moving together, each following its own path but all bound by the same gravity, orbiting through the shared halo of dark matter that envelops them. Their motion would be slow, almost imperceptible on human timescales, but steady. Over millions of years, the pattern would shift, orbits tightening, some satellites drifting closer, others falling inward, their shapes stretching as the Milky Way's pull grows stronger. The system would look alive, not static, a dynamic dance of light and motion unfolding over cosmic time. In the broader context of the universe, the Milky Way's satellites are modest things. but they represent the same processes that occur everywhere. Every large galaxy has companions like these, remnants of its formation and sources of future growth. Together they form the scaffolding of cosmic structure, the small building blocks from which everything larger is made. The universe builds its complexity layer by layer, from the smallest scales upward, and the satellite galaxies are the fossils of that process. For astronomers, these satellites also offer a kind of laboratory. Because they're small and relatively simple, they allow scientists to study the physics of galaxy formation in environments that are easier to model. They help constrain theories about dark matter, whether it's cold, warm, or something else entirely. They also provide insight into how feedback processes, like supernova explosions and stellar winds, affect the evolution of galaxies. In a way, they're the testing grounds for our understanding of cosmic evolution. By studying the smallest galaxies, we learn about the larger structures in the universe. Even though most of them are faint and invisible without powerful instruments, the satellites still shape our galaxy's destiny. Over billions of years, some will spiral inward and merge, adding their stars to the Milky Way's outer halo. Others may remain in orbit indefinitely, continuing to trace slow paths through the darkness. Their collective gravity contributes subtly to the Milky Way's overall motion through space. Their presence adds texture and depth to the galaxy's surroundings, making the region around it more than just empty space. A living, evolving system of interconnected parts. The space between these satellites is not empty either. It's filled with the same diffuse gas, the same dark matter, and the same magnetic threads that pervade the rest of the galactic halo. Streams of material flow between them, sometimes pulled from one satellite to another, sometimes drawn toward the Milky Way itself. These faint connections are the veins and arteries of the galaxy's extended structure, carrying matter and energy across vast distances. They ensure that even the most distant satellites are not isolated, but part of a continuous whole. As we move through this understanding, it becomes clear that what surrounds our galaxy is not a boundary, but a network, a collection of smaller systems linked by gravity and time. The satellites are the outermost lights of that network, the last visible nodes before the darkness of intergalactic space. Beyond them lies the great wilderness between galaxies, a realm even more diffuse and mysterious, where matter thins almost to nothing, and yet still holds faint traces of structure. That's where the halo ends, and the universe begins to stretch outward into the intergalactic medium. Far beyond the bright disk of the Milky Way, past the glowing spiral arms and the faint shimmer of the halo, there are places where stars no longer belong to any one structure. They drift in long, graceful lines through the darkness, tracing paths that loop and curve around the galaxy like quiet ribbons of light. These are the stellar streams, the faint rivers of stars that weave through the outer halo, marking the routes of long-vanished galaxies and clusters that once orbited the Milky Way. They are the remnants of the galaxy's past encounters, the lingering echoes of collisions stretched and thinned by gravity, until they form the delicate, continuous trails that wrap around the sky. If the Milky Way could be seen from outside, these streams would be among its most haunting features. Ghostly arcs of light looping around its edges, faint but unmistakable, telling stories of how the galaxy came to be what it is. A stellar stream begins when something small crosses the path of something large. A dwarf galaxy, perhaps, or a globular cluster, a dense sphere of ancient stars bound tightly by gravity, wanders too close to the Milky Way. The larger galaxy's gravitational pull begins to tug at the smaller one, pulling on one side more strongly than the other. Over time, those differential forces stretch the smaller system, drawing stars away from its edges. Some of those stars fall inward, others outward, and slowly a long trail begins to form. The central body continues to orbit, but its stars are now being peeled off, left behind in a continuous line that follows its path. What was once a compact cluster, or a small galaxy, becomes a thread of light, a stream of stars moving in silent formation across the galactic halo. These processes happen so slowly that to human senses they seem frozen. But across cosmic time, they are constant, graceful motions like currents in a deep ocean. The Milky Way is surrounded by dozens of such streams, each one tracing an orbit through the halo, each one the remains of something that was once distinct. Some of them are long and nearly circular, wrapping around the galaxy like rings. Others are shorter, more chaotic, broken into segments where the stars have dispersed. They vary in brightness, in density, in age. Some are so faint that they can only be seen through careful analysis of stellar positions and velocities in large sky surveys. Yet together they form a vast network, a living map of the Milky Way's gravitational field. One of the best known of these streams is the Sagittarius stream, the same remnant mentioned before, born from the ongoing merger of the Sagittarius dwarf galaxy. It's one of the largest and brightest stellar streams, wrapping nearly halfway around the Milky Way in a looping arc. Its stars are scattered over a vast region of the sky, from the direction of the galactic centre all the way to the opposite side. Observing it is like looking at the handwriting of gravity itself. Every curve, every twist, every faint knot marking a point in the long conversation between galaxies. The Sagittarius stream is still being replenished as the dwarf galaxy continues to lose material, which means it's not just a relic of the past but an event still unfolding, slowly but continuously, right now. Other streams are more subtle, but no less significant. The GD1 stream, discovered in 2006, is one of the longest and thinnest known. It stretches across more than half the sky, composed of stars that were once part of a globular cluster destroyed long ago. Its path is so narrow and sharply defined that it serves as a precise tracer of the Milky Way's gravitational field. By studying the way it bends and kinks, astronomers can detect the influence of unseen masses, perhaps clumps of dark matter that have passed through it, distorting its shape. In that way, streams like GD1 act as instruments of measurement, revealing the structure of what we can't see through the behaviour of what we can. Another stream, called the orphan stream, has no clearly identifiable parent body, at least not anymore. Its stars move together, following an orbit that suggests they once belonged to a small galaxy now completely dissolved. It's long and faint, a remnant without a source, the last whisper of a system erased by time. There are others too. The Palomar 5 stream, born from a globular cluster of the same name, the Phoenix and Hermes streams, winding faintly through the outer halo, and countless smaller unnamed threads waiting to be discovered. Each one is a scar left by gravity, a visible reminder that the Milky Way is not static but constantly reshaping itself through these slow, consuming encounters. These streams are beautiful not just because they are graceful, but because they are records. They hold within them the story of the galaxy's assembly, written in the language of motion. When astronomers measure the orbits of the stars within them, they can reconstruct where those stars came from, when they were stripped from their original systems, and how they have moved since. The combined picture that emerges is one of continual change. A galaxy built not all at once, but through an ongoing series of mergers and absorptions, each leaving behind a faint trace. The streams are the evidence of that process, preserved across billions of years. They are history made visible. Some of these streams may one day disappear entirely, their stars dispersed so widely that they blend indistinguishably into the halo. Others will remain coherent for eons, slowly wrapping around the galaxy as their orbits precess. Each one evolves according to the same physical principles: gravity, inertia, and the tidal forces that shape them. In some cases, the interaction between streams can reveal new details about the distribution of mass in the galaxy. When two streams cross or bend near one another, their motions can indicate where dark matter is clumped, how the halo is shaped, and how it changes with distance from the galactic centre. the Milky Way's invisible structure becomes perceptible through these faint threads, like the way a spiderweb becomes visible only when dust or dew settles on its strands. The existence of these streams also tells us something about the resilience of stars themselves. Even when their original systems are destroyed, the stars survive. They continue their orbits, following the same paths they once shared, keeping their cohesion through the shared momentum of their origin. They are survivors of disruption, their light a soft testimony to the balance between destruction and persistence. In that sense, they're not just remnants, they're continuations, the living legacy of systems that were transformed but not lost. To imagine these structures properly, it helps to scale the picture in your mind. The Milky Way's disk is about 100,000 light-years wide. The halo stretches far beyond that, several 100,000 light-years, and the longest streams can span a comparable distance. If you could see them all at once, the galaxy would appear as a glowing disk, surrounded by loops and arcs of faint starlight, extending outward like threads of silk in every direction. The pattern would not be symmetrical or uniform. Some regions would be densely populated with overlapping streams, others nearly empty. The overall impression would be one of motion, a galaxy surrounded by a slow, graceful whirl of its own history. The stars within these streams are old, most of them billions of years in age, but their light still carries information about their origins. By studying their chemical compositions, astronomers can distinguish between those that came from globular clusters and those that came from dwarf galaxies. Stars from clusters tend to be more chemically uniform, while those from galaxies show greater variation, reflecting more complex histories of star formation. These differences allow scientists to classify the streams and understand the diversity of systems that contributed to the Milky Way's growth. It's like tracing the genealogy of the galaxy, identifying which ancestors contributed to which parts of its structure. The streams also interact with the Milky Way's other components. As they pass through the disk or the inner halo, they can be perturbed by giant molecular clouds or by the gravity of spiral arms. These encounters create subtle oscillations and distortions in the streams, leaving behind wave-like patterns. By measuring these disturbances, astronomers can learn about the masses and positions of objects that would otherwise be invisible. Even the influence of dark matter subhalos, small concentrations of dark matter with no stars, can be detected this way. When one of these invisible clumps passes near a stream, it creates a gap or a kink in the distribution of stars, a quiet sign of its passing. Through these effects, the stellar streams become tools not only for studying history, but for exploring the present structure of the invisible universe. The discovery of these streams is relatively recent. Many were first identified in the early 2000s, when digital sky surveys began mapping the positions of millions of stars with high precision. The Gaia mission, launched by the European Space Agency, revolutionized this work by providing detailed measurements of the positions, motions, and brightness of more than 1 billion stars. With Gaia's data, astronomers can trace the movement of individual stars across the sky and identify those that share common paths. The result has been the revelation of a vast network of streams, far more extensive than anyone had imagined. What once seemed like an empty halo is now recognized as a dynamic, structured environment filled with the remains of countless smaller systems. The Milky Way's streams are not unique. Other galaxies show the same patterns. When we look at the Andromeda galaxy through powerful telescopes, we can see faint arcs and filaments of stars extending outward from its disk. The same kind of rivers of light created by tidal interactions. Even dwarf galaxies have smaller-scale versions of these streams, evidence that the same processes occur on every level of cosmic structure. It's a universal phenomenon, a signature of how gravity shapes the universe over time. Galaxies grow by merging, and each merger leaves behind its trace. The streams are those traces, stretched thin by motion, preserved by time. The names we give them, Sagittarius, Orphan, Palomar, are convenient. but they also hint at their character. They are like orphans in a way, no longer belonging to their original homes, yet not entirely lost. They are bridges between systems, connections between what once was and what now is. Their stars move through the halo like memories drifting on slow currents, still following the paths laid out by forces that acted billions of years ago. They remind us that nothing in the universe ever truly disappears. It only changes form. If you could watch one of these streams over millions of years, you would see its stars gradually spread out, the stream elongating and thinning until it fades into the general population of the halo. But even then, the memory of its orbit would persist. The stars would still share similar motions, and their distribution in space would still reflect their origin. In that way, the galaxy's history is preserved not just in light, but in motion, in the patterns of how stars move through space, long after the visible structures have dissolved. Sometimes, when astronomers simulate the Milky Way's evolution, they watch these streams form in accelerated time. The models begin with a smaller galaxy approaching the Milky Way. As it draws closer, tidal forces begin to stretch it. A few million years later in simulation time, the first stars begin to peel away, forming a faint tail behind it. Then another, stretching ahead of it. As the orbit continues, those tails lengthen and wrap around the galaxy. The smaller galaxy shrinks, its core slowly unraveling until it's gone, leaving only the streams. The process looks almost gentle, almost inevitable. In real time, it's a process that takes billions of years, far beyond any human sense of duration, yet it continues always, reshaping the Milky Way one small encounter at a time. These rivers of stars show that the boundary between galaxies and their surroundings is porous, always shifting. Stars are not confined to their original homes. They move freely under gravity's guidance, forming new patterns as old structures dissolve. The Milky Way's edge, if it can even be defined, is not a hard line, but a region of transition, a place where the galaxy's material begins to mingle with the larger environment of the local group. The streams flow through that region like tributaries feeding a larger current, connecting the Milky Way to the intergalactic medium and to the space beyond. As you think of these rivers winding through the dark, it becomes easier to sense the galaxy not as a single object, but as a process, a continuous act of movement and transformation. The disk spins, the stars orbit, the satellites circle, the streams flow. Everything moves together in one vast choreography, held by gravity but shaped by time. The streams are simply the visible expression of that motion, the delicate filaments that make the invisible currents of the galaxy visible for a while. And as those currents carry us farther outward, the question of boundaries returns. Where does the Milky Way truly end? Where does its influence fade into the intergalactic sea? As you move outward, past the last faint rivers of stars that loop around the Milky Way like traces of memory, the sense of structure begins to fade. The brightness of the disk is long gone now, the glow of the spiral arms has dimmed into a distant blur, and even the scattered streams that mark the remnants of old collisions become harder to trace. The stars grow fewer, the space between them widens, and slowly the idea of the galaxy as a single, defined thing begins to dissolve. What's left is the question of boundaries, not in the human sense of borders drawn sharply, but in the quiet, gradual sense that exists in the universe, where one thing blends into another so gently that it's hard to tell where it stops. The Milky Way, like every galaxy, doesn't end suddenly. It fades, layer by layer, until what remains is a field of solitary stars surrounded by the unseen gravity that still holds them loosely in place. Defining where a galaxy ends might seem like a simple thing, but it isn't. In space there are no walls, no edges, no physical markers separating one region from another. The stars that belong to the Milky Way are bound by its gravity, but that binding isn't absolute. The farther out you go, the weaker it becomes, and at some distance the pull of other galaxies, or the general expansion of the universe itself starts to compete. Beyond that point, the stars and gas are no longer securely held. They drift freely through the void, their orbits no longer closed around the galactic centre. Astronomers sometimes define that point as the edge, but in truth it's more a threshold, a gradual fading of belonging. Our galaxy's visible disk stretches roughly 100,000 light-years across, but its gravitational influence extends much farther. The halo of dark matter and diffuse gas that surrounds it may reach out to nearly 1 million light-years from the centre, perhaps halfway to the Andromeda Galaxy. Within that enormous volume, the Milky Way's gravity dominates, though it grows weaker with distance. This entire region, filled with faint stars, globular clusters and satellite galaxies, can be thought of as the true extent of the Milky Way's domain. Yet even that boundary isn't fixed. It shifts slightly over time as matter flows in and out, as gravitational interactions pull some stars away and capture others. The stars that inhabit this outer region are among the loneliest in the galaxy. Many of them were born elsewhere, torn from smaller galaxies during ancient mergers and left to drift in long, looping orbits. They move slowly, hundreds of thousands of light years from the nearest dense cluster of stars. If you stood on a planet circling one of those distant suns, the night sky would be mostly dark. The Milky Way would still be visible, but only as a faint glowing arc, a narrow ribbon of light stretching across the horizon, distant and pale. The familiar constellations would be gone, replaced by sparse points of light scattered unevenly across the sky. The nearest neighbouring stars would be so far apart that light from one might take centuries to reach another. It would be a view of isolation, of space drawn out to its fullest scale. Even in that vast emptiness, the Milky Way's presence can still be felt. Gravity reaches far, and even the faintest motion of a distant star carries the imprint of the galaxy's pull. Astronomers can use these motions to measure the shape and extent of the Milky Way's gravitational field, defining a boundary not by light, but by influence. The stars that move too fast, that seem to be escaping, mark the transition between the bound and the unbound. That threshold, known as the escape velocity boundary, isn't sharp, but it helps define the outermost region where the galaxy's gravity can still hold sway. Beyond it, stars drift away forever, becoming part of the larger population of intergalactic space. The concept of belonging becomes abstract out here. Inside the disk, it's easy to say that stars belong to the Milky Way. They orbit in organised paths, they participate in its rotation, they contribute to its structure. But in the halo, motion becomes less orderly. Stars move in eccentric, tilted orbits, some looping in from great distances, others just passing through. Some belong to the galaxy in a loose temporary way, bound only for a time before gravitational nudges send them away. Others have already left but are still near enough that they appear to linger. The outer halo is full of such transitional stars, caught between belonging and drifting, between being part of something and being free of it. Astronomers often describe the boundary of a galaxy in terms of density, the point where the number of stars or the concentration of matter drops below a certain level. But again, this is only a convention, a human attempt to impose a definition on something continuous. The reality is that the Milky Way blends into the larger structure of the local group, the collection of galaxies that includes Andromeda, Triangulum, and dozens of dwarfs. Between them lies a shared field of dark matter, a common gravitational envelope that connects all three. From that perspective, the Milky Way doesn't end at all. It simply transitions from its own halo into the collective halo of the local group, its individual identity dissolving into the shared mass of the system. That blending is not just theoretical, it can be observed in motion. The Milky Way and Andromeda are moving toward each other, drawn by their mutual gravity. Their halos already overlap, even though their visible disks are still 2.5 million light-years apart. Somewhere in the space between them, the gravitational influence of one gives way to the other, but there's no line dividing them. The stars and dark matter in that region move under the combined pull of both galaxies. It's a place of shared belonging, a region where definitions lose meaning. In a few billion years, the two galaxies will merge entirely, forming a new, larger system. When that happens, the boundaries we describe today will vanish altogether. Even now, before that merger, the outskirts of the Milky Way are not static. They're shaped by constant flux, by infalling gas, by the slow accretion of material, by the occasional capture of small galaxies. The boundary is porous, allowing matter to flow inward and outward. Streams of hydrogen drift toward the disk, feeding future star formation, while radiation and stellar winds push other material outward. The balance between these processes determines the size and structure of the halo. In some regions, the gas density is high enough to form faint filamentary clouds. In others, it's so thin that a single atom might occupy a cubic meter. Yet even those isolated atoms are part of the galaxy's extended reach, bound by its gravity even if barely noticeable. The stars that inhabit this space are difficult to study, but when we do observe them, they tell stories about the galaxy's past. Many of them are extremely old, with compositions that suggest they formed in the earliest phases of galactic assembly. Some may even predate the Milky Way itself, having originated in smaller systems that merged to form it. Others are younger but were ejected from the disk by gravitational interactions or by the violent outbursts of supernova. These runaway stars travel outward, slowing gradually as they climb away from the galaxy's centre, sometimes reaching distances of hundreds of thousands of light years before stopping. Some eventually fall back, pulled once more by gravity. Others cross the escape boundary and continue into intergalactic space. The escape of stars from the galaxy is a slow but inevitable process. Every interaction, every gravitational encounter, transfers energy between stars. Occasionally one star gains enough energy to exceed the escape velocity and is flung outward, leaving the galaxy behind. Over billions of years, this creates a faint population of intergalactic stars, solitary travellers that wander the space between galaxies. These stars, though few, are another form of the Milky Way's boundary. They represent the outermost extension of its history, the faint glow of belonging stretched thin until it breaks. Even as they move beyond its reach, their origins remain traceable. Their motions, their compositions, their trajectories all carry the signature of the galaxy that once held them. In that sense, the boundary of the Milky Way is not a place but a process. It's the constant interplay between what is bound and what is not, between what remains and what drifts away. The galaxy grows and erodes at the same time. It gathers material from its surroundings even as it loses stars to the void. The result is a balance maintained over cosmic time that defines the Milky Way's identity. It's not a static object but a dynamic equilibrium, always changing, always redefining itself through motion. The concept of belonging, when applied to galaxies, mirrors something familiar in smaller scales. Just as people belong to families, communities, or nations not by fixed lines, but by shared influence and interaction, so too do stars belong to galaxies through the invisible ties of gravity and motion. There's no single point where belonging ends. It's a gradient of connection that weakens with distance, but never disappears entirely. Even a star wandering between galaxies is still part of the larger web of the cosmos, its motion linked to every other through the shared fabric of gravity. The universe doesn't create isolation, it creates continuity. The outer halo, with its faint stars and diffuse gas, is where that continuity becomes visible. It's a transition zone, not empty but sparse, not bound but not yet free. It's where the Milky Way's presence fades into the background of the universe, and yet it's also where the threads connecting us to the larger cosmic web begin. The same forces that hold these stars loosely to our galaxy also connect the Milky Way to the network of galaxies beyond. Through those connections, energy and matter flow on scales far beyond anything we can see directly. The galaxy's edge, then, is not an end but a bridge, a threshold where local structure meets universal structure, where the idea of ours becomes meaningless in the face of something larger. If we could somehow see this region with perfect clarity, it would appear neither empty nor sharply defined. Instead, it would shimmer faintly, filled with scattered stars, tenuous gas, and faint glows of ionized hydrogen. Filaments of material would stretch outward, linking the Milky Way to nearby galaxies. The boundary would look more like mist than like a line, a gradual thinning of light into darkness. The stars would drift at different speeds and directions, some falling inward, others moving outward, all part of the same subtle current. You could follow those currents outward until the gravitational influence of the Milky Way became indistinguishable from that of the local group as a whole. The local group itself has a kind of shared boundary, a region where the pull of its collective gravity balances against the expansion of the universe. That point marks the limit of what can remain bound together over cosmic time. Beyond it, galaxies drift apart with the general flow of cosmic expansion. Within it, gravity wins, keeping the Milky Way, Andromeda, Triangulum and their satellites connected. In that sense, the true boundary of the Milky Way isn't just the edge of its halo, but the edge of the local group, the outermost region where its gravity still contributes to the larger balance of forces that defines this small island in the universe. In the long future, after the Milky Way and Andromeda merge, that boundary will change again. The two galaxies will form a new system, often called Milkomeda in theoretical models, and its gravitational reach will extend even farther. Its halo will be more massive, its stars more dispersed, and its boundary less distinct. Over trillions of years, as the universe continues to expand and distant galaxies move beyond the horizon of visibility, that merged system will become increasingly isolated. Eventually, it will exist as a single gravitational island in an otherwise dark universe, its boundary defined only by the faint glow of its remaining stars and the invisible sea of dark matter around them. Even then, the question of belonging will persist, though the scale will have changed. For now, though, the Milky Way's boundary is alive with motion. Stars cross it in both directions, gas flows inward and outward, and the halo continues to evolve. The streams, the satellites, the companions, all of them participate in this slow exchange. It's not a static shell enclosing the galaxy, but a living region of interaction. When we think of what surrounds the Milky Way, this is one of its most important layers, the zone of transition between the galaxy itself and the intergalactic medium beyond. It's the place where gravity still whispers but no longer commands, where belonging turns to drifting, and where the history of the Milky Way begins to merge with the wider story of the universe. Beyond the outermost stars of the Milky Way, past the slow drift of the halo and the last faint loops of its stellar streams, lies a region so empty that the human mind struggles to imagine it. This is the intergalactic wilderness, the vast space between galaxies, where matter thins to almost nothing, and light travels for millions of years before finding anything solid to touch. From a distance, the universe might appear full. The images we see from telescopes show clusters of galaxies, luminous and crowded, connected by glowing filaments of gas and dark matter. But these images are deceiving. They compress enormous volumes of space into flat pictures. The reality is that even in the richest clusters, galaxies are separated by distances so great that they never touch. Between them lies a silence so deep that it defines the very texture of the universe. If you could travel out there, leaving the Milky Way completely behind, the first thing you would notice is the growing stillness. Inside the galaxy, even in the outer halo, space is full of motion. Stars orbit, gas flows, magnetic fields ripple. But once you cross into the intergalactic region, that motion begins to fade. The density of matter drops until, on average, there's only one atom in every few cubic meters. the gas that remains is ionized, meaning it's stripped of its electrons by the radiation from galaxies and quasars. It isn't the kind of gas that could ever form stars or planets. It's more like a trace, a whisper of the early universe still echoing between the galaxies. This intergalactic medium, as astronomers call it, fills most of the volume of the universe. It's invisible to the naked eye, but it can be detected through its effect on light. When photons from distant quasars, bright energetic cores of remote galaxies, travel through space, they pass through countless thin clouds of this gas. Each cloud absorbs specific wavelengths of light, leaving behind a series of tiny dips in the quasar's spectrum. This pattern, known as the Lyman alpha forest, is one of the main ways scientists study the intergalactic wilderness. It reveals the presence of the otherwise invisible matter that stretches between galaxies, forming a vast, interconnected network that mirrors the cosmic web of dark matter. Even though it's diffuse, this medium isn't empty of structure. It forms filaments that extend for hundreds of millions of light years, linking galaxies and clusters into a single cosmic framework. Between these filaments lie enormous voids, vast regions with almost no matter at all, where the density drops even lower. These voids can span tens or even hundreds of millions of light years, and within them galaxies are rare. They are the quietest places in existence, regions of near nothingness where time seems to stretch unbroken by any sign of change. To travel through one would be to experience distance on a scale so great that meaning itself would start to dissolve. The gas that fills the intergalactic medium is ancient. Much of it has been there since the universe's earliest moments, left over from the era just after the Big Bang. In those early times, matter was distributed almost evenly throughout space. As the universe expanded and cooled, tiny fluctuations in density began to grow under the influence of gravity. Over billions of years, these fluctuations formed the structures we see today: galaxies, clusters, filaments, and voids. But not all matter collapsed into galaxies. Most of it remained between them, heated and thinned by radiation and cosmic shocks. That matter, still floating between galaxies, is the main constituent of the intergalactic wilderness. Within this vast expanse, temperature and density vary depending on location. In the dense filaments connecting galaxies, the gas can reach temperatures of millions of degrees, heated by the shock waves from the formation of clusters. In the voids, it's much cooler, often only a few thousand degrees above absolute zero. These differences form a kind of cosmic landscape, though not one we could ever see directly. There are no landmarks, no horizons, no up or down, just gradients of density and heat stretching endlessly across space. If you could float there, somewhere in one of these intergalactic filaments, you would see almost nothing with your eyes. The nearest galaxy might be millions of light years away, visible only as a faint smudge. The background sky would be dark but not completely black. The combined glow of distant galaxies and the faint light of the cosmic microwave background, the residual radiation from the Big Bang, would provide a dim illumination, a uniform glow filling all directions. It would be light too faint to cast shadows, too smooth to distinguish, but it would be everywhere. You would be surrounded not by emptiness, but by the soft afterglow of the universe's birth. The intergalactic medium plays a quiet but crucial role in cosmic evolution. It acts as the reservoir from which galaxies draw their gas and the space into which they expel material through winds and jets. When supernovae explode, or when black holes in galactic centers release energy, some of that energy escapes into intergalactic space, heating and stirring the surrounding gas. Over time, this process enriches the medium with heavier elements, oxygen, carbon, iron, produced inside stars. Though sparse, the intergalactic gas now contains traces of all the materials needed for planets and life. They are spread too thin to coalesce on their own, but they're present nonetheless, diffused across unimaginable distances. In some regions, the intergalactic gas forms faint, glowing structures detectable in X-ray or ultraviolet light. These structures, often associated with clusters of galaxies, mark where matter has gathered under gravity's pull. The largest of them are known as the warm-hot intergalactic medium, or WIM, a term that describes gas with temperatures between 100,000 and 10 million degrees. The WIM is thought to contain much of the universe's missing baryonic matter, the normal atomic material that cosmological models predict should exist, but that wasn't accounted for in galaxies and stars alone. Detecting this hot gas requires careful observation, but where it's found, it completes the picture of the universe's mass distribution, confirming that the cosmic wilderness is far from empty. These filaments and clusters form part of what astronomers call the large-scale structure of the universe. On these scales, galaxies are not isolated points, but nodes in a vast network, connected by threads of gas and dark matter. The Milky Way is one of those nodes, part of a filament that also contains Andromeda, Triangulum, and many smaller galaxies. Together they form the local group, which lies along one arm of an even larger structure, the Laniakea supercluster. This supercluster contains hundreds of thousands of galaxies spread across 500 million light-years, all moving collectively under the influence of gravity. The intergalactic medium is the space between those galaxies, the invisible foundation on which the entire structure rests. When scientists map this structure using redshift surveys and computer simulations, the result looks remarkably organic. A web of filaments and knots, like veins or neural pathways stretched across space. The bright spots are galaxies and clusters, the filaments are intergalactic gas and dark matter, and the voids are the empty spaces between them. This cosmic web is the skeleton of the universe, the framework that defines where matter gathers and where it doesn't. The Milky Way, like every other galaxy, is just one point along that web, surrounded by filaments of gas that connect it to the wider cosmos. It's strange to think that the space between galaxies, which seems so empty, is also what connects them. The same gravitational fields that hold galaxies together also extend across intergalactic space, shaping the motion of matter on enormous scales. When one galaxy pulls on another, that force is transmitted through the dark matter and gas between them. The intergalactic medium acts as the medium of interaction, a kind of cosmic environment that links everything together. Even though the distances are vast, the universe behaves as a connected whole. The wilderness between galaxies is not isolation, it's the connective tissue of the cosmos. The light that travels through this space carries its history. Photons that left distant galaxies billions of years ago pass through the intergalactic medium on their way to us, interacting with the gas along their paths. They're redshifted by the expansion of the universe, stretched into longer wavelengths, cooled as space itself expands. By the time they reach Earth, they carry with them the imprint of everything they've passed through. When astronomers measure that light, they can reconstruct not only the history of the galaxies that emitted it, but also the properties of the space in between. In this way, the intergalactic wilderness serves as both a backdrop and a record, the quiet archive of everything that has happened since the universe began. Within this wilderness, galaxies are the exceptions, not the rule. They are islands in a vast sea, small concentrations of matter amid the overwhelming emptiness. The distances between them are so great that, if scaled down, a galaxy the size of a coin would be separated from its nearest neighbour by kilometres of space. Yet despite that separation, the universe is not fragmented. The cosmic web ensures continuity, with gravity linking every part to every other. The intergalactic medium flows along those filaments, carrying gas from one region to another, feeding galaxies and clusters as it goes. The flow is incredibly slow. Millions of years to move across a fraction of a filament, but it never stops. It's the universe's long, steady breath. In the largest voids, where even that flow becomes negligible, there is almost nothing. These are regions so underdense that a single cubic meter might contain only a few atoms, Light crosses them almost unimpeded, its path unchanged for billions of years. The voids are not completely empty though. Faint tendrils of gas and dark matter still pass through them, invisible but real. They are the universe's calmest places, regions of almost perfect stillness. If the Milky Way were somehow placed in one of these voids, it would be completely isolated. There would be no nearby galaxies, no incoming gas, no gravitational interactions. It would drift alone, its stars slowly fading over time, its structure preserved only by its own gravity. Yet even the emptiest voids play a role in cosmic evolution. They expand faster than denser regions, driven by the overall expansion of the universe. As they grow, they push matter into the surrounding filaments, reinforcing the structure of the cosmic web. In this way, the voids and filaments evolve together, shaping one another. The intergalactic wilderness is not static. It's a living structure, constantly changing under the combined influence of gravity, radiation, and cosmic expansion. When astronomers look at this structure as a whole, they see that galaxies like the Milky Way occupy a special place, not at the centre of anything, but along the middle ground between extremes. We are not in a cluster, nor in a void, but along a filament, connected to both. The space that surrounds us, the intergalactic wilderness, is both the emptiest and the most connected region imaginable. It is empty enough to seem lifeless, yet full enough to link the universe together. From a philosophical perspective, the existence of this wilderness is a reminder of scale. The distances involved dwarf anything human. Even the fastest spacecraft ever built would take longer than the age of the universe to cross the gap between galaxies. And yet, the same physical laws that govern an atom or a human being govern these immense spaces too. The same gravity that holds us to Earth also shapes the motion of galaxies across millions of light years. The intergalactic wilderness may be vast beyond comprehension, but it is not separate from us. It's part of the same continuum, the same universe, obeying the same principles. If you could listen to it, if there were a way to translate the faint motions of the intergalactic medium into sound, it would not be silent. The variations in density, the flow of gas along filaments, the expansion of space itself, all would create a kind of deep, slow rhythm, far below the range of hearing. It would be a rhythm measured in billions of years, the background pulse of the cosmos. The wilderness may appear still, but it's alive with motion too slow for our senses to perceive. The boundary between the Milky Way and this intergalactic wilderness is gradual, just as the boundary between one galaxy and another is. The halo's diffuse gas and the intergalactic medium blend together, sharing material and motion. Streams of gas flow outward, while others flow inward. Radiation from stars and quasars keeps the gas ionized, maintaining a delicate balance between cooling and heating. The Milky Way is not a closed system. It's an open participant in this exchange, breathing in and out through its boundaries. As you picture this vast, quiet expanse, the feeling of isolation shifts into something else. Not emptiness, but connection. The intergalactic wilderness is the medium through which galaxies communicate, even if that communication happens in the slow language of gravity and light. The photons that cross this space are messengers, carrying information from one corner of the universe to another. The atoms that drift through it are travellers, part of a circulation that spans cosmic time. What seems like nothingness is, in truth, the backdrop of everything. The sea on which all galaxies float, the context that gives their existence meaning. If you could step back far enough from the universe to see everything at once, you would find that it doesn't look like the black emptiness we often imagine. Instead, it has structure, immense, delicate, and connected. What surrounds our galaxy and all galaxies is part of this greater design, the cosmic web. It's the largest structure known to exist, a vast network of filaments and nodes made of galaxies, dark matter, and gas, stretching across hundreds of millions of light years. Every galaxy we can see, from the smallest dwarf to the largest spiral, lies somewhere along these threads, linked by the invisible gravity that binds the cosmos together. The name cosmic web isn't poetic exaggeration, it's an accurate description. When scientists simulate the universe's evolution using computers, starting from the near uniform state after the Big Bang, a pattern naturally emerges. Matter doesn't spread evenly. Tiny fluctuations in density, seeded by quantum variations in the early universe, grow over time under the influence of gravity. The denser regions attract more matter, forming filaments and clusters, while the emptier regions expand into voids. The result, after billions of years, is a web-like structure, long interconnected strands of matter surrounding vast dark cavities. The filaments are where galaxies form, connected at nodes that correspond to clusters and superclusters. The voids are the spaces in between, the cosmic wilderness seen from an even greater distance. Our galaxy sits within one of these filaments, part of a region of the web called the Laniakea supercluster. This enormous structure spans about 500 million light-years and contains hundreds of thousands of galaxies. The Milky Way, Andromeda, Triangulum, and their smaller companions occupy a small branch of this larger system, which itself flows toward an even greater concentration of mass, a gravitational centre known as the Great Attractor. Every galaxy in Laniakea is moving in response to that pull, though the distances are so immense that these motions are measured in tens of millions of years. The entire structure is in motion, part of the universe's slow, expanding dance, yet bound together by gravity's subtle cohesion. If you could see this web with your eyes, it would be faint and intricate, like a three-dimensional map of light and shadow suspended in the dark. The filaments would appear as faintly glowing threads, each dotted with galaxies. The clusters at their intersections would shine more brightly, the concentrated points where hundreds or thousands of galaxies gather. Between them, the voids would stretch vast and black, regions where matter is scarce and time seems unbroken. It would look organic, not mechanical or symmetrical, but irregular and natural, like frost patterns spreading across glass or the branching of roots beneath soil. Every filament would connect to another, and through them all the same invisible forces would move. Dark matter forms the backbone of this web. Though it doesn't emit light, it makes up most of the universe's mass and dictates how visible matter is distributed. The galaxies and gas we can see are merely the luminous tracers that reveal dark matter's underlying shape. Without dark matter, the universe would not have formed the large-scale structures we observe. Its gravity pulled ordinary matter into the filaments, where it cooled and condensed into stars and galaxies. Every visible structure, every spiral, cluster and nebula is an expression of that invisible framework. The cosmic web is, in essence, the architecture of gravity itself. The scale of it defies comprehension. The filaments stretch for hundreds of millions of light years, yet they are only a few million light years thick. The nodes at their intersections, the galaxy clusters, can contain thousands of galaxies, each one holding billions of stars. The distances between these clusters are so vast that light takes hundreds of millions of years to travel from one to another. And yet, across those unimaginable distances, the web remains coherent. It's not static. It evolves slowly over time as matter continues to flow along the filaments into the clusters, feeding their growth. The web is dynamic, a living structure shaped by the interplay of gravity, expansion, and time. Our understanding of this structure comes from both observation and simulation. In the 1980s, astronomers began mapping the positions and redshifts of galaxies in large surveys. When these maps were plotted in 3 dimensions, a pattern emerged. Galaxies were not scattered randomly but arranged in sheets and filaments. The discovery was one of the great revelations of modern cosmology. It showed that the universe had a texture, that its matter was organised in a pattern extending across cosmic scales. Later surveys, such as the Sloan Digital Sky Survey, refined this picture, revealing ever more detail, vast filaments stretching across billions of light years, enormous walls of galaxies, and immense voids between them. Computer simulations, using the known laws of physics and the measured parameters of the universe, reproduce this pattern with remarkable accuracy. They begin with a nearly uniform field of matter, with small fluctuations corresponding to the density variations imprinted by the early universe's inflationary expansion. Over time, under gravity, these fluctuations grow. The denser regions collapse first, forming filaments, while the less dense regions expand. When scientists compare these simulated webs with actual galaxy maps, they find a near-perfect match. The cosmic web is not just an idea, it's a direct consequence of the universe's evolution from its earliest moments. Every filament in this web carries matter from the voids toward the clusters, guided by gravity. The process is slow but relentless. Galaxies within the filaments move gradually toward the nodes, merging and combining as they go. Gas flows along these same paths, feeding star formation within the galaxies. On these scales, galaxies are not static islands, but participants in a continuous flow, moving through a cosmic river that spans the universe. Even dark matter, though invisible, moves with this flow, its distribution changing slowly as the web evolves. The cosmic web also shapes the behavior of galaxies on smaller scales. Galaxies within filaments tend to align their spins with the filament's direction, while those near nodes may have spins oriented differently due to the complex flows of matter. This large-scale alignment, subtle but measurable, shows how deeply connected everything is. Even the orientation of a single galaxy's rotation can trace back to the structure of the cosmic web around it. The Milky Way's position within its filament influences its motion, its interactions with neighbours, and even the flow of gas that sustains its star formation. When we observe the universe at its largest scales, we see that it's not uniform but patterned. The distribution of galaxies traces an underlying order, not imposed but emergent. It's the result of physical laws operating over unimaginable spans of time and distance. Gravity, acting on the primordial fluctuations left by the Big Bang, naturally produces this web. The simplicity of that cause and the complexity of its outcome are one of the universe's most striking features. From basic laws arises structure of extraordinary beauty. The voids between the filaments, though nearly empty, play their own role. As the universe expands, matter flows from these underdense regions into the denser filaments, reinforcing the pattern. The voids grow larger and emptier, while the filaments become denser and more defined. Over cosmic time, this process will continue, though at an ever-slowing pace, as dark energy drives the accelerated expansion of the universe. Eventually, the distances between superclusters will grow so great that they will no longer interact gravitationally. The cosmic web will remain, but its filaments will stretch, its connections will weaken, and isolated clusters will drift apart, surrounded by widening voids. In the present universe, however, the web still connects everything. The light we see from distant galaxies travels along these filaments, sometimes scattered or absorbed by the intergalactic gas they contain. The same gas acts as a medium for cosmic magnetic fields, which extend along the filaments, linking galaxies through invisible lines of force. In some regions, these magnetic fields guide the motion of charged particles, creating subtle synchrotron emissions detectable by radio telescopes. These observations provide further evidence that the web is not only gravitational but electromagnetic, a structure of both matter and energy. When we map the cosmic web, we also map our place within it. The Milky Way's filament connects to others that stretch toward the neighbouring clusters like Virgo and Hydra. Those in turn connect to even larger structures, eventually leading toward the massive concentrations of galaxies that dominate the observable universe. The entire system is nested, one level inside another, like layers of a single organism. From within, it's impossible to see the whole, but from the perspective of data and simulation, we can glimpse its coherence. Every galaxy, no matter how small, contributes to the overall structure. Every filament is part of a greater whole. The cosmic web provides the context for everything we know. Stars, planets, and life exist within galaxies, but galaxies themselves exist within the web. The flows of matter along its filaments determine where galaxies form, how they evolve, and how they cluster. Even the distribution of dark energy, the mysterious force driving cosmic acceleration, is studied in relation to this structure. The web is the reference frame for the universe, the stage on which every event unfolds. It's worth remembering that what we see of the web is only the illuminated fraction. The galaxies mark its densest regions, but most of the mass lies in the invisible dark matter and faint gas that fill the spaces between them. The visible universe, the one we can photograph, is just the glowing outline of a much larger unseen structure. It's like watching a city at night from an airplane. You see the lights of the streets and buildings, but not the air, the ground, or the invisible infrastructure that connects everything together. The cosmic web is that infrastructure, extending far beyond the reach of light. As our instruments improve, we're beginning to see more of this hidden structure. Deep field surveys with sensitive telescopes have revealed faint filaments of gas connecting galaxies, glowing weakly in ultraviolet and X-ray light. Observations of the cosmic microwave background show subtle distortions caused by the gravitational lensing of these filaments, confirming their presence even where no visible galaxies exist. Every new observation adds detail to the map, filling in the spaces between what we once thought were isolated systems. The more we see, the clearer it becomes that the universe is a single, interconnected whole. In a way, the cosmic web redefines what it means for something to be around our galaxy. The Milky Way isn't surrounded by emptiness. It's embedded in a filament of matter that connects it to countless others. These same forces that shaped our galaxy also shaped every other galaxy in the web. We are not at the centre, nor at the edge, but along one of its many strands, a participant in the universe's continuous structure. Everything we see, from nearby stars to the most distant quasars, exists within this framework. The scale of this structure makes the notion of isolation meaningless. Every atom in our galaxy, every particle of gas in the halo, every photon of light leaving a star is part of a network that spans the entire observable universe. The cosmic web isn't just what surrounds us, it's what we are within. It's the scaffolding of existence, the unseen lattice that holds everything in place. From the smallest dust grain to the largest galaxy cluster, everything owes its position, its motion, and its history to the web. If you could drift far enough away to see the whole thing, you might realize that the universe is not random but deeply coherent. The same laws that shape the web's vast filaments also govern the tiny structures inside galaxies. The same gravity that binds the Milky Way to its companions also organizes the cosmic web across billions of light years. The pattern repeats, scaled upward, an expression of the same fundamental principles applied to different magnitudes. The universe, in all its immensity, follows a single simple logic, one that expresses itself in forms both grand and small. The cosmic web is not static, though. It's still evolving, still changing. The filaments continue to draw matter inward, feeding the clusters at their intersections. Galaxies continue to merge and form new stars. Gas continues to cool and condense along the filaments, while radiation and feedback from stars and black holes reshape the surrounding medium. It's a slow, continuous process that has been underway since the first billion years after the Big Bang, and will continue for trillions more. The web is the universe's ongoing story, written in the movement of matter across time. And as we follow that story outward, we reach the point where the web itself becomes indistinguishable from the background of the universe. The filaments fade into the overall expansion, their contrast diminishing as dark energy accelerates the separation of structures. The galaxies within each filament remain bound, but the distances between filaments grow, stretching the web thinner. The universe continues to expand, and the light from distant regions takes longer and longer to reach us. Eventually, beyond a certain distance, that light will never arrive. The expansion will outpace it. The observable universe will shrink, not in size but in visibility, and the cosmic web will recede into darkness. Even then, though, the structure will persist. The filaments will remain, the clusters will endure, and the galaxies within them will continue their motions, unseen but still connected by gravity. The web will still be there, even when we can no longer see it. It will still surround whatever remains of the Milky Way, still defining the universe's shape on every scale. And from within that framework we find our place again, a single galaxy, surrounded by its halo, its companions, its streams, and its boundaries, all embedded within this greater network. Everything that surrounds our galaxy is part of this web, extending outward without limit, linking the Milky Way to everything else that exists. If you could drift back now, inward through all the layers you've just travelled, through the long threads of the cosmic web, past the filaments and clusters, past the wide voids and the thin rivers of gas that stretch between galaxies, you would begin to see the faint, familiar glow of home returning. It would appear first as a barely perceptible haze, then as a curved shimmer of light, then as a distinct disk, the Milky Way. Not the image on a textbook page, not a name in a catalogue, but the vast, living system you've been tracing outward from all along. You would see it now as one among many, suspended within the larger architecture of the universe, and yet still singular, the place that gives every star you've ever known its context. From out here, looking back, the galaxy seems quiet. Its spiral arms are faintly luminous, turning slowly, their motion imperceptible except over millions of years. The central bulge glows with a warm light, the combined radiance of billions of aging stars, and the outer disk stretches thinly into darkness. Around it, you can see the soft shimmer of the halo, a pale sphere of ancient stars and diffuse gas. Even farther out, faint lines trace where the tidal streams wrap around it, the remnants of smaller galaxies folded into its gravity. Beyond those, the Magellanic clouds circle gently, their arcs trailing wisps of gas, and all of it sits within the faint glow of the local group's shared halo, linked invisibly to Andromeda and Triangulum by the long gravitational threads that join them. It's strange, from this vantage point, to realise that almost everything we've ever observed lies within a single small region of that structure. All the stars visible to the naked eye, every nebula seen through a telescope, every point of light that has guided navigation or inspired imagination, all of it comes from this one spiral, this one disk of stars orbiting a black hole 40,000 light-years from the centre. The immensity of the galaxy is itself a kind of illusion. To us it feels infinite, but it's just one component in a still greater whole. That perspective doesn't diminish its beauty, it deepens it. If you continue to look closely, you can begin to see the patterns of motion that shape it. The stars move in orbits defined by gravity, each tracing its own path around the galactic centre. The gas clouds swirl along the spiral arms, forming new stars as they compress and cool. Clusters drift together in slow arcs, globular systems orbit in long looping ellipses, and dark matter permeates it all, invisible yet essential. The Milky Way is alive with motion, every component linked to every other through gravity's silent coordination. Nothing here is still, though the scale of its movement makes it seem so. Our solar system is a tiny part of this, a speck orbiting near one of the spiral arms, about 27,000 light-years from the galactic centre. The Sun moves at roughly 200 kilometers per second, completing a full orbit every 230 million years. That means since the solar system formed, it has circled the galaxy about 20 times. Each pass brings it through different regions, past the dense star fields of the arms, through the quieter inter-arm spaces, into and out of the galaxy's midplane. Over those long cycles, the Milky Way itself has changed, absorbing smaller galaxies, forming new stars, releasing others into its halo. The place we call home has never stayed the same. If you trace your gaze farther outward from the solar system, you begin to sense how much of what surrounds us is dynamic and interconnected. The heliosphere, inflated by the solar wind, merges with the interstellar medium of the local bubble. The bubble connects to others, forming a patchwork of cavities carved by ancient supernovae. Those in turn blend into the diffuse gas of the galactic disk, which extends into the halo, which dissolves into the intergalactic medium, which merges with the filaments of the cosmic web. There is no clear point where one ends and another begins. Every layer fades into the next. Every boundary is a gradient. The structure of the universe is continuous, without interruption, from the smallest scale to the largest. Looking back at the Milky Way from this perspective, it becomes easier to understand that galaxies are not isolated entities but events, ongoing processes rather than static things. The Milky Way is a temporary configuration of matter, constantly changing as it exchanges material with its surroundings. Stars form, evolve, and die. Gas flows in and out. Dark matter provides the unseen structure that holds it all together. What we call a galaxy is really a system in motion, a balance maintained by the same laws that govern everything from atoms to clusters of galaxies. Even its beauty, the spiral arms, the luminous core, is the visible expression of those dynamics. If you were to observe it over billions of years, you would see it change shape. The spiral arms would shift, new ones forming as old ones fade. The central bulge would grow as stars migrate inward. The halo would thicken with the debris of absorbed satellites. Eventually, far in the future, the Milky Way will meet Andromeda. Their disks will merge, their stars will intermingle, and the result will be a new kind of galaxy, likely elliptical, round and smooth, its spirals long gone. From within, it will still feel familiar, but from afar it will look like something else entirely. Even then, it will not be the end of anything. The cycle will continue, just on a different scale. For now, though, our galaxy remains what it has been for billions of years, a vast rotating collection of stars, gas and dark matter held together by gravity's balance. It's easy to think of it as a place, but it's more accurate to think of it as a process, an unfolding. Every part of it, from the dense star clusters near the core to the faint drifting stars in the outer halo, participates in that process. The Milky Way is not an object surrounded by space. It's a pattern within space, an organised flow of matter within a larger whole. The scale of it is almost beyond comprehension, yet it's still made of the same ingredients that make up everything else. Hydrogen, helium, a scattering of heavier elements, the same materials that form planets, clouds, and living beings. The difference is only in arrangement and scale. The stars shine because of the same nuclear processes that happen in the sun. The clouds of dust and gas that drift between them are made of the same atoms that exist in the air we breathe. The universe is not composed of separate substances, it's one substance, organised differently in different places. From this understanding comes a kind of quiet continuity. What surrounds our galaxy also surrounds us. The same space that lies between the stars extends through the solar system and around the Earth. There is no barrier separating us from the cosmos, only differences in density and scale. The night sky is not a window looking out from one world into another. It's a view across the continuous fabric of the same world, the same universe, from a different vantage point. The boundaries exist only in our perception. If you imagine looking out from the edge of the Milky Way, the rest of the universe appears not as something beyond, but as something connected. The nearest galaxies shimmer faintly, their light travelling for millions of years to reach here. The farther ones form patterns that trace the filaments of the cosmic web. Beyond them, the faint glow of the cosmic microwave background marks the limit of what light can show, the horizon of the observable universe. But even that horizon isn't a wall. It's simply the limit of time, the distance light has been able to travel since the beginning. Beyond it, the same universe continues, stretching farther than we can see or measure, governed by the same laws. The realization that there's no true boundary between here and there, between our galaxy and the rest, changes the way we understand location itself. Where becomes relative. The Milky Way is somewhere within a filament, the filament within a supercluster, the supercluster within the universe, and yet each part is complete in itself, containing the whole in miniature. The shape of a spiral galaxy echoes the shape of the cosmic web. The flow of gas within a nebula mirrors the flow of matter along filaments. The patterns repeat, not because of design, but because the same physics applies everywhere. Looking out from home, we begin to see how deeply connected everything is. The gravity that holds our feet to the Earth is the same gravity that binds the galaxy together. The light that warms the atmosphere comes from nuclear reactions identical to those happening in every star across the universe. The atoms in our bodies were once part of stars that lived and died billions of years ago. Their material recycled into new forms. There is no separation between us and what we see when we look at the night sky. We are part of it, made of it, shaped by it. If you were floating here, at the edge of the galaxy, the view would feel both infinite and intimate. The Milky Way's disk would stretch beneath you like a vast glowing river, its stars blurring together into a continuous light. Beyond it, you'd see Andromeda as a faint spiral, another island of stars moving slowly closer. The space between them would appear empty, but you would know it's full, of dark matter, of gas, of faint stars too distant to see, of light travelling endlessly. It would be quiet, but not still. The motions of the galaxies, the flow of the intergalactic medium, the background expansion of space, all would be continuing, unnoticed by human senses but constant nonetheless. The light from Earth, if you could see it from here, would be unimaginably faint. It would blend with the light of the sun, which itself would be indistinguishable from a million other stars scattered across the disk. Yet that tiny point, that minuscule glow, would contain everything familiar, the oceans, the continents, the lives of billions. From this scale, it's impossible to separate the personal from the cosmic. The same laws, the same matter, the same history extend across all scales. Home, seen from here, is both insignificant and extraordinary, a single instance of the universe reflecting on itself. The longer you look, the more the distinctions fade. The Milky Way becomes one of countless spirals. The local group becomes one of countless clusters. The cosmic web extends without end, its filaments receding into the distance. And yet within all that immensity the same principles hold. Light travels, matter moves, gravity shapes. The universe doesn't change its rules, it applies them universally, producing everything from the simplest atom to the grandest structure. What surrounds our galaxy is not emptiness but continuity. It's a series of relationships between stars and space, between galaxies and filaments, between the visible and the unseen. Each layer leads naturally to the next, each one dependent on the others. The Milky Way is part of that chain, and so are we. Every breath we take, every photon we see, every atom in our bodies is part of the same ongoing exchange. The universe is not something outside of us. It's something we're within, something we're made of, something we're participating in. If you let that idea settle, the feeling it brings isn't smallness, but inclusion. The scale is vast, but the connection is direct. We exist within the same framework that shapes galaxies and stars. We are not separate observers looking out into the universe. We are the universe looking inward at itself, aware for a brief moment of its own structure. The Milky Way surrounds us, the local group surrounds it, the cosmic web surrounds them, and beyond that lies everything still unknown. The layers are endless, but they are all one system. From the quiet of this perspective, the boundaries dissolve completely. Home is not a single point, not a single planet or even a single galaxy. It's the continuum of everything that exists, from the smallest grain of dust to the farthest cluster of galaxies. To look out from home is to look outward and inward at once, to see the same universe reflected in both directions, continuous, coherent, and whole. And as that understanding deepens, the motion continues. The galaxy keeps rotating, the stars keep shining, the light keeps travelling through the dark, the cosmic web keeps stretching and evolving, the universe keeps expanding. There is no final moment, no still point, no ending to reach. Only the quiet, ongoing flow of everything surrounding us, including us, and extending far beyond our sight. And now, as we drift back from all those scales, from the quiet spaces between galaxies, through the faint halo of our own, and back toward the small patch of sky we call home, it's easy to forget how far we've travelled in thought. The distances are too vast to hold all at once, but that's what makes it peaceful. The universe doesn't ask to be understood in its entirety, it only asks to be noticed, one layer at a time. Every star above, every stretch of dark between them, every invisible thread of connection, it's all part of the same single structure we're inside right now. So wherever you are, whether you're listening to rest or just to drift, you can let the idea settle that you're already surrounded by everything you've just imagined. The galaxy, the streams, the filaments, they aren't out there somewhere. You're within them. The same matter, the same light, the same time. Every breath you take is part of the Milky Way's quiet motion. Every moment of stillness here belongs to the same universe you've just been exploring. If you found calm in this journey, in the slow pace of it, the distance, the steady unfolding, you can stay here for a while. Let the sound of it fade into your own quiet. The stars will still be moving, the galaxy will still be turning, and all the light that fills the universe will still be travelling, softly, endlessly, through the dark.